Now I think we can also start.
Okay. So.
Wait.
I'm not in a hurry, so.
Yes, fine. I just want to give people the chance to move between sessions. Yeah, and then so maybe the next speaker during the question time, the next speaker can already come to the front and wait, and then and quickly connect, change the. All right, so welcome again to that session. And the first speaker is Davide here. He's going to give us.
Oh, sorry. I don't know what is happening here. Fuck. Okay, maybe now is okay. So, hello everyone. I'm Ario Altamura. I'm doing my PhD at the University of Trieste, and I'm working on collapse models in quantum mechanics and test of these models. In particular, non-interferometric tests of these models using rotational degrees of freedom. So, okay. I want to give you a brief introduction about these models. So, these are, in standard quantum mechanics, you have the Schrödinger evolution and then some collapse happens when you measure your system. Here, these dynamical reduction models are some models in which you have a unique equation for accounting for the reduction of the wave function and also the Schrödinger evolution. And this should be done in a way so that you don't have linear superposition of macroscopically different states, and it must not contradict any of the quantum mechanic results in the microscopic regime. How you do this? You take the Schrödinger equation, you include some additional terms, stochastic and nonlinear terms. This will cause the collapse of the wave function. Moreover, this reduction is amplified for macroscopic systems. And moreover, you need both of these terms, because if, for instance, you have only nonlinear terms in the wave function, you can create some protocol to do nonlinear, faster than light signaling. So then the general structure of the collapse equation for a continuous reduction of the wave function is the one that you can see here. So you have some unitary evolution and then other two additional terms. Here you see you have these AI operators. These are called collapse operators. And you see here you have the mean value of these operators. And this is the source of nonlinearity of the equation. Moreover, you have here these linear processes. And so you have stochasticity into the equation. For instance, here I'm looking at a white noise. And then you have some parameter, gamma, that measures the strength of this collapse. Then you take this equation, you evaluate the equation for the density matrix, and you end up with this kind of equation with this double commutator in the collapse operators. Okay, then you can choose these operators in order to specify what is your collapse. In this case, in this continuous spontaneous localization model, your operator are the mass density operator. So you have a system composed of n particles. Each of the particles has a mass which is distributed according to this law. So you see there you have this Gaussian with the xj operator that is the position operator of each of the particles of the system. And then if you plug this operator into the master equation, you get this equation that you can see here. Here you have lambda and RC, which are the two free parameters of the model. So the aim at the end is to constrain this parameter with the experimental tests. And lambda stands for the rate of this collapse, and RC has to do with the smearing that you can see in the mass density operator. And this equation predicts the diffusion in the center of mass motion for both rotational and translational degrees of freedom. So then I'm focusing on rotational dynamics, so you can derive some Langevin equation for the orientation of your system. So here, for example, I'm considering an harmonic oscillator with some dissipation, some thermal noise, and additional to this, the contribution coming from the model that you can see there on the right, this tau CSL. And it is possible to predict the correlation function for this noise that will be, in this case, delta correlated in time, and has this eta parameter that will depend on lambda, on RC, and on the mass density distribution of your system. In this case, yes, the Fourier transform of this quantity. So on the shape of your system. Then this is the exclusion plot. So you have two free parameters, RC and lambda. You try to do some tests to constrain these parameters. This is from 2022. And you can see here, in general, you can use interferometric tests to prove these models, because, okay, you can prepare some superposition and say, okay, if there is this collapse, this fundamental collapse, at some point this superposition will decay, but they are not so strong in constraining these parameters. So the strongest bounds are coming from non-interferometric tests. So for example, you see on the right, these blue regions are obtained looking at the data from gravitational wave detectors, for example. The one with the darker color is from LISA Pathfinder, from looking at the vibrational degrees of freedom of LISA Pathfinder. So my work basically is focused on how you can get an optimal setup for detecting such effect. And okay, the first experiment we looked at was this one performed by Lee and others in 2020. This was meant to be a test of the gravitational potential, the Newtonian gravitational potential, but we used the data from this experiment to place a bound on the parameters. So this is a good system because it's a torsion pendulum, so the rotational degrees of freedom generally couples less with environmental noise. Moreover, it is a macroscopic system, so as I told you in the beginning, there is an amplification of the effect if you work with a macroscopic system. And moreover, if you look at the bottom here of this image, the test mass in this case has this pattern that you can see here. This is a planar picture of the pattern that is in the test mass. So this is a periodic test mass in the density. So you have these two regions, the orange and the blue one, which have different densities. And we discovered that this can be used to enhance the collapse effect in some region of the parameter space. And this was already discovered for the vibrational degrees of freedom in 2018. Okay, then we considered also LISA Pathfinder, because last year they published the data for the rotational dynamics, so the rotational noise affecting the setup. And so this is a macroscopic mechanical system. Moreover, is a space experiment, so you have a high sensitivity. And okay, then how you set the bound? Because I'm telling you, okay, you can set a bound if you look at the noise acting on the system. And so you take the spectral noise density, in this case for the torque. You can predict one from the model, the CSL model, and then you look at the experimental data, take the floor noise, and you compare the two. So in this case, for LISA, the spectrum was in the acceleration of the rotation, and then you have to transform to torque, but then you can compare the two spectral density. And okay, in the end, we end up with a bound that was stronger than the one that was obtained with the translations with the same experiment. So how you understand this effect? In the end, the fact is that in this kind of experiment, the test mass are confined in this cage, let's say, and then the residual gas inside the experiment is colliding multiple times, and these collisions are correlated. So in the end, the effect is stronger on the translations, so on the translational noise, than on the rotation. And then you can see that if you take into consideration this parameter alpha, which is the ratio between the spectral density for the torque and the spectral density for the force, you can say that the rotations are better than translations to place a bound on the parameters if alpha CSL is bigger than alpha experiment. And you can see here these two examples with a gas confined, a system in an infinite volume of gas, and a system confined in a finite box. In the case on the right, you see there are a lot of values of RC and L. L is the size of the object, of the cube in the case of LISA Pathfinder, for which the rotations are better than translations. And then, okay, in the end, this is the bound on the parameter. So the region in light blue at the top was the one excluded using the experiment, but then you can try to change the parameters, the mass density, the shape of the object in order to get an optimal setup. And then I want to compare the red curve, that was the one obtained in this work from 2025, with the previous one that was still from LISA data, Pathfinder data, but using translational degrees of freedom. And so, okay, this is a brief summary, and thank you for the attention. If you have any questions.
Thank you very much. So, are there questions?
No questions.
Any questions? So, hi.
What's your opinion on the prospect of completely excluding CSL models?
I think that, okay. Yes. So I think that lately there was some other experiment, like a few weeks ago, that was about X-ray emission. So you have some sample, because of this noise, you have some, you expect more emission of photons from this sample, and I think they were able to exclude a lot of the remaining region, also the value that was predicted by Ghirardi, Ribini, and Weber, the one you see here on the left. So I think is going to be done in a short period of time, yes. But then if you want to extend the model, let's say here I'm taking into consideration just white noise. There are also a colored version of the noise if you think that this kind of noise is coming from a physical process. And so that's it. Okay.
So for your tests, would it be better to have a system, small system that can rotate very quickly, or a large system that can rotate only slowly?
I mean, depends on the. I need like a large system because, as I said, the collapse is affected by the number of molecules and particles in the system. But the region you can exclude with an experiment is dependent on the dimension, the characteristic dimension of the system. So if in the case of LISA, L is like centimeters. You see that here the minimum in this bound is between 10 to the minus 2, 10 to the minus 3 RC. So you should have an object that is has some characteristic dimension, let's say the periodicity or something like this, that has that dimension of the RC that you want to test, let's say. So smaller RC to explore the region near 10 to the minus 6, that should be the most interesting one.
Okay. So thanks. Let's thank the speaker again. And then,
yes. Okay.
So after 10 minutes, I show you the full hand, right? But that's including the questions.
Yeah,
right?
sure.
Okay, cool. So our next speaker is Devashi Das. So he's starting now.
Yeah, good afternoon, everyone. First of all, I would like to thank the organizers for giving me this opportunity to present my work here. Today, I will present a new experimental proposal to test the non-classicality of gravity. So this talk will be based on this publication, this paper, which was published last year, October. So far a lot of work has been done to construct quantum theory of gravity, or what would be the generic features of a quantum theory of gravity. But these theories are very difficult to be verified in the laboratory. On the other hand, we address a much easier question, whether gravity is quantum at all. And this question is still empirically unsettled. We still don't know whether gravity is quantum or classical. And so to address whether gravity is quantum or not, first we have to fix what do we mean by quantum mechanics. So quantum mechanics is composed of various postulates. For example, there is superposition principle, unitary time evolution, quantum measurement postulate. And in 2017, an experiment was proposed to test the validity of these first two quantum aspects in the context of gravity. And our new proposal aims to test the validity of quantum measurement postulate in the context of gravity. So these are the two papers where the 2017 proposal was presented. So let me briefly recapitulate the 2017 proposal. Here two masses are considered, and these two masses are initially in product state. Each of these two masses are held in spatial superposition L plus R, and by experimental design it is ensured that the dominant interaction between these two masses is gravity. Now, starting from a product state, if after a certain time entanglement is generated between these two masses, then it will prove non-classicality of the dominant interaction, which is gravity in the present case. Why? Because there is a well-known principle in quantum information theory which tells that local operations and classical communication cannot create entanglement. And from our point of view about natural interactions, we assume that all the interactions in nature are local. There is no action at a distance type interaction. And if we assume this, then all the operations that are performed on the two masses are local. Then entanglement generation can only be explained if the interaction or communication between the two masses is non-classical. So this is the essence of the 2017 proposal. Later, in these two papers by Carlo Rovelli, Kaslav Bruckner, it was shown if in this type of experiment gravity-induced entanglement is witnessed, then it will prove that gravity obeys superposition principle. But as I mentioned earlier, superposition principle alone does not define the whole of quantum mechanics. There are other postulates as well. So, if we observe gravity induced entanglement in such an experiment, then there are two possibilities. First, gravity obeys quantum mechanics, or gravity obeys some other non-classical theory that we do not know till date that supports superposition principle. To know whether gravity is exactly quantum mechanical or not, we need to test more and more quantum mechanical postulates in the context of gravity. And motivated from this, our proposal aims to test another postulate, which is quantum measurement postulate in the context of gravity. So, there are different aspects of quantum measurement postulate. For example, quantum measurement induced collapse or disturbance, and this specific aspect we aim to test in our present proposal. Other aspects are there is always one measurement outcome in a single run, but this is always observed. There is nothing quantitative to test here. And the outcome probabilities are given by the Born rule, mod psi square, but we are not aiming to test Born rule in the context of gravity in our proposal. So, first we have to define what do we mean by classical field. So, classical field is number valued at each point in spacetime. So, at each point in spacetime has a number. It is not operator valued, and one can always in principle measure those number values arbitrarily accurately without any disturbance. So, these two conditions of a classical field gives rise to the non-disturbance condition or NDC of classicality. This NDC implies that the act of performing an intermediate measurement should not influence the outcome statistics of a subsequent measurement. So, for example, if we watch a football match, our act of observation should not have any effect on the result of the football match. So, this is based on our classical worldview. So, this NDC or non-disturbance condition was originally proposed by Koffler and Kassler-Bruckner in 2013. So, now let me state our proposal in a very schematic way. We consider a mass which is denoted by this blue sphere, and it is subjected to an interferometer. And this interferometer will create a special superposition L plus R of the mass. Here L is the state of the mass passing through the left arm of the interferometer, R is the state of the mass passing through the right arm of the interferometer. And at the end of the interferometer, the outcome plus or minus is detected. This is one part of the experiment. In the other part of the experiment, everything remains the same, except we place a detector in the midway of the interferometer that performs measurement on the gravitational field produced by this mass. So, here there are two key points. One, the mass is quantum mechanical because we are creating a special superposition with the mass, but it is large enough to produce a detectable gravitational field at the position of this detector. Next, this intermediate measurement is indeed on gravity. It is not a direct position measurement by electromagnetic interaction or by photon scattering. It is on the gravitational field of this mass. Now, according to the definition of our definition of classicality, if gravity is classical, then this intermediate measurement on gravity should be possible without causing any disturbance. That means the final outcome statistics in the first case, when no intermediate measurement on gravity is occurred, should be equal to the final outcome statistics in the second case after the intermediate measurement on gravity. On the other hand, if these two statistics are not equal, then it will imply gravity is not classical. Why? Because it will imply that this intermediate measurement on gravity is causing some disturbing effect on the state of the gravitational field, which in turn causing a disturbing effect on the mass configuration, and that disturbance on the mass configuration is detected through the final measurement. So, this is actually a schematic. The actual proposal is quite complicated compared to this, but due to time constraint I am not going into the details of the actual proposal. I will just mention that this is the source mass, the red denoted by red arrow. The source mass is placed in a superposition. In the first part, after closing the superposition, a final out measurement is performed. In the other part, instead of one, we place two detectors sequentially, and each of these two detectors are nothing but again a mass in spatial superposition. And these two detectors performs two sequential measurement on the gravitational field of this mass denoted by this red curve. And by adjusting the distance between the source mass denoted by this capital M and the probe and each of these probe mass, we can indeed ensure that these intermediate measurements are on gravitational field of this source mass. And here sequential probe mass are taken in order to make this experiment loophole free, in particularly to reduce the clumsiness loophole of the experiment. So now let me state what type of mass we should take. If we take mass of the source and each of the probe to be 10 to the power minus 14 kilogram, the superposition size of the source mass and the probe mass of the order of 250 to 450 micron, separation between the source and the probe, each of the probe of the order of 157 micron, and if we take the interaction time between the source and the probe to be of the order of 2 to 3 seconds, then we can guarantee enough detectable non-classicality, in the sense enough large violation of the no signaling, no disturbance condition. So here it is crucial to note that we have fixed the separation between the source and each of the probes to be 157 micron, because for such separation it can be shown if we take the each of the mass neutral, then also there will be some electromagnetic interaction between the neutral masses, which is Casimir interaction. But if we take the separation of this order, then it will ensure that gravity is significantly stronger than the electromagnetic interaction between the masses, and this will ensure that the intermediate measurements are indeed on the gravitational field. These are not on electromagnetic field. So there are several experimental advantages of our proposal compared to the 2017 proposal. Our proposal works for any decoherence rate, which was not the case for the 2017 proposal, and our current proposal does not require any trusted measurement device. It was also not the case for 2017 proposal. So for both the 2017 proposal and our new proposal, we need mass of the order of 10 to the power minus 14 kilogram or 10 to the power minus 15 kilogram. The initial requirement is that we need to prepare a pure state, and that step has already been realized for such mass scale by various experimentalists worldwide using ground state cooling. And this actually make this type of experiments very promising for near term realizability, because the initial requirement has almost achieved by different experimentalists. After that, we need to create a spatial superposition, but this step is really challenging, and experimentalists are trying to realize this step. So to conclude, whether gravity is quantum or classical, we still don't know. The 2017 proposal can test whether gravity obeys quantum superposition principle. Our new proposal can test whether gravity obeys quantum measurement postulate. And these two tests together can take us towards some more complete demonstration of gravity as a quantum entity. And compared to the 2017 proposal, our new proposal has several experimental advantages. With this, I would like to thank all of you.
Interested in asking a question? Yeah, so often these kind of theories, tests are very theory dependent, right? So it's not really theory agnostic, of course, what is, right? But, so in some sense,
we assume some definition of classicality.
There's dichotomy, you say it's either classical or it's completely quantum. So I would ask, did you also look at something like stochastic gravity? Because you make statements like you're saying that if the statistics of the experiment changes, then gravity has to be quantum.
Right.
So is that a general statement that you can make at all? They compare with theories?
It is general depending on the fact that we have assumed this definition of classicality. We have to define something. What do we mean by classical? Otherwise, we cannot tell what is non-classical. So this is our definition of classicality, and this definition of classicality comes naturally from our classical point of view. We cannot prove that this is classical, but this is our definition. This is a starting point.
Right. So then it would be really interesting from my perspective to now apply this, also with your experiment in the background of your proposal, and look at different theories.
Right.
And say, do they fulfill, are they classical by your
Right.
definition?
Right.
I find it. So any other questions?
Yeah, Leggett-Kirk inequality, yeah. Two instant of time. We have taken the definition of classicality from Leggett-Kirk, and then we used this condition, which can be derived actually from this condition. This condition was derived in this paper by Koffler and Bruckner. This is an easier test compared to the Leggett-Kirk test, and here the interpretation is very straightforward. Violation implies measurement-induced disturbance. That's all.
Okay, yes, let's thank Gabashi.
Yeah, thank you. Oh, sorry.
You also get a microphone for the online audience.
Can you put it? Yeah. Okay.
Hello? Is it working?
See your background?
No, I meant the microphone. No, I can't really hear you.
Do you mean the online microphone?
Yeah.
Yeah, no, it's working. Just share.
Okay. Yeah, so this should be fine. Slideshow.
Does that work? Yeah, it works.
Okay.
All right, perfect. Yes, so let's come to our next talk by Kwon. Please, the stage is yours.
Okay, I don't know whether to. Oh, I'm holding this?
Yes, you hold that.
Both. Oh, okay. Yeah, kind of want a cursor, so I don't know if to stand or sit. But okay, so some of you have come here last year or the year before, heard me talk about these crazy experiments to detect holography before. This time I actually came with my experimentalist collaborator who is sitting right there. So I am going to try to talk about everything but the experiment. And as you know, gravitational wave detectors such as LIGO and Virgo have enabled a new era in multi-messenger astronomy. And we've now also had multiple smaller high-frequency interferometers such as the holometer at Fermilab, Quest at Cardiff, and GQuest at Caltech, and also a prototype interferometer at INRIM. So I want to talk about a multimodal search in holographic quantum gravity, connecting primordial CMB signatures to quantum gravitational fluctuations today. Okay. And as I often do, I want to start off by pointing there is something very wrong with the standard field theory picture in vacuum energy. It's 122 orders of magnitude off, the worst prediction in physics. And Cohen, Kaplan, Nelson bound. Okay, how do I get a cursor? Do I have some way of finding a cursor? Okay, I guess I'll have to do without. Thank you. So that shows what the problem is. If you just count the possible states of QFT in a vacuum, those scale like the volume, and since black hole entropy, of course, scales as the area, then the virtual states of the vacuum can actually become a black hole, which means that we really need to take holography seriously, even in flat space, because if you count all the background degrees of freedom, there's simply too much information. And if you want to reduce it sufficiently, you introduce large quantum correlations. And let me make it clearer where this infrared problem is. So on this diagram, this is a black hole, and this is a quantum, and it's mass versus system size. And this line is where the Cohen-Kaplan-Nelson bound is. So the states allowed in low energy flat space QFT actually scales as r to the 1.5th power, which is a lot less than r to the 2nd power. And there is an elegant essay by Wald about how QFT is missing these background correlations. Basically, to create a consistent QFT, we do renormalization, which is basically subtracting an infinity that corresponds to vacuum energy. But that process includes assumptions about the background spacetime, about the global metric that requires you to know how that subtraction is done for all the other modes everywhere else. So even for a free field, the background has a dynamic causal structure that is globally coupled to all the other quantum states via gravity and inherits their non-local nature. So we get to our central hypothesis, which is that these causal structures fluctuate from dynamic gravitational coupling to vacuum energy at roughly a Planck random walk, which is very large. In standard theory, these are incoherent, but in the holographic theory, the background correlations allow them to add coherently. And let's skip this. And now, last time I talked about this, because I always try to give a conceptual talk, people seem to find the lack of familiar equations from standard holography quite troubling. So I thought I would bring this back to the intro to holography that Rob Myers gave last year. Some of you might remember this. The first law says that if you define this modular Hamiltonian, which is just the log of the density matrix, then the change in entanglement entropy is the change in the expectation value of the modular Hamiltonian. Now, Tom Banks and Catherine Zurek have found a new universal conjecture that the fluctuations in the modular Hamiltonian are equal to the entanglement entropy. And if this is true, then all causal diamonds, even in flat space, have uncertainties like black hole horizons, which is like a Planck random walk if you look at this Merolf quote here, or citation here. And this is actually a generalization of a result that Cassini, Horta, and Myers did in 2011. And it applies broadly to causal diamonds in flat space, the cosmological horizon of DS, and Ryu Takayagi diamonds on the boundary of ADS, but not to diamonds or black holes that are in the interior of ADS. And it's because here the role of the ADS space is actually taken on by the causal diamond scale. And remember, in ADS, the boundary scale controls the non-locality, the information density, and the UV to IR relationship. So you might want to look at this roadmap if you're interested. And yeah, maybe it would have been better if I gave this overview last year after Rob's talk, but I only thought to do this after we had a nice lunch talking about this at some length. So yeah. And now if you see such a conjecture as a quantum gravity theorist, you immediately ask, well, what's wrong with my standard graviton 2-point correlation like Dan Carney, who's speaking tomorrow, did in his recent paper? And so here's Tom's answer. Basically, you want to use unitarity, so you want a non-Lorentz invariant gauge. And the only gauge invariant things in gravity are scattering amplitudes at infinity, and this is finite space, so you want a gauge in which the time slices stay within the causal boundary, which is now not translation invariant, and we don't know of such a gauge. So now, what do these correlations actually look like? There's a fascinating model of black hole information by Gerald et al., who originally proposed the holographic principle. He takes a quantum state at the horizon, calculates the gravitational frame dragging across the horizon, and finds it entangled with another state at the antipode, and with a sign flip. And now we've ended up with eigenstates that are non-locally extended across the whole horizon. And Zurek and colleagues have mapped these onto a causal diamond in flat space using radially accelerated coordinate frames with Rindler horizons. And then they reproduce the answer using all these different methods. Yeah, and this was originally going to be after Sharmila's talk, but due to technical difficulties, I'm going to have to kind of preempt this. So Sharmila will talk about probing some of one of Zurek's models with interferometer data. And I just wanted to clarify that only an ad hoc heuristic version of the model is currently tested. All of the rest are the more fundamentally derived models are not tested. And that's because the theory describes a commutator between incoming and outgoing null coordinates, but these are actually operators. Right? So for an observational signature, you need to model the state reduction that happens in a quantum measurement, and that hasn't been done. The operator description should accommodate scale invariant non-local correlations with arbitrarily large coherent scales based on the measurement. But the only predictions we have from Zurek so far use effective field theory to map these onto metric fluctuations along one direction. So any effective field theory that is indistinguishable from a classic stochastic fluctuation with a finite coherent scale by construction cannot be holographic. Okay, so now how do we want to actually probe this thing? I put an interferometer here, so I'm clearly going to build a LIGO or Virgo. But first, you note that there are these spherical harmonics, and one distinct feature of the et al. Model is that because of the antipodal antisymmetry, you only get the odd modes in the expansion. And this antisymmetry might have shown up in the CMB. It's a great testing ground for avoiding the measurement problem because everything freezes in at the horizon. And there's like a 1 in 1,000 preference for odd modes over even modes. And in this temperature correlation, there is an exact 0 at 90 degrees. And this is a map where we remove the effect of galaxy masking. It was also recently found that galaxy distributions contain some parity violations, which is not a field theoretic p-symmetry violation. And we tried to rewrite inflation with primordial quantum modes on causal boundaries. So the standard inflation uses field modes on this surface, which is totally acausal. And we want to quantize modes on this surface, the horizon. And here's a diagram of 4D spacetime in conformal coordinates. Basically, our observer is here. This is the end of inflation. The CMB comes from this sphere. And then we take this causal diamond, which has coherent fluctuations, and say, what's the very last causal diamond that connects with this one? And then we take the footprint of these two causal diamonds, and then we look at their overlap and look at the angular scales here, right? And suddenly, these show up in the data. So this is the even modes only, because the CMB measurements have an unknown dipole subtracted. So we want a clean parameter-free test, so we only do the even modes. And then you see this super, super clean 0, right? And the Planck models are even cleaner than the WMAP models. And in comparison, random realizations of the standard model are all over the place. So there's a huge preference for our types of models. You can also do this with odd modes included, treating the dipole as a tunable parameter and just doing the best fit for each model, and it shows the same preference. We also tried mapping the CMB correlations onto flat spacetime by basically taking out the conformal expansion, after which the conformal causal structure is basically identical between flat space and inflation. So you take this pink line, and then you get this pink line, which is now for a interferometric signal and the angular distribution of fluctuation power in it. And this purple line is my theory model that was developed more than a year earlier, mostly using the 't Hooft algebra. As you can see, they match pretty well. And in comparison, the Zurich spectrum is quite different. But again, I emphasize that this is only the heuristic model based on effective field theory and not one of her more fundamentally derived theories. And in the frequency domain, the two spectra look quite different, similar. So you actually really need to focus on the interferometer geometry and the detector coupling to these different modes during the measurement. These spectra reflect what we can do on a 6 by 6 meter table, but they're not for the same geometry. This one's for a simple Michelson, and this is for a 3D geometry that probes more the transverse dimension of these spherical harmonic modes. But a big advantage of these 6 meters tabletop scale is that we can probe a lot of different geometries, different correlation structures, or we can even modulate the spectrum later if we have a signal. And I'm going to skip the rest because Hartmut's going to tell us about the experiment himself. I want to leave with this, which is a very long but non-exhaustive list of the growing body of work predicting a quantum gravity signal in laser interferometers. And there's this entire class of graviton noise models, including one from our very own Hing-Tong Cho and Bei-Lok Hu. And the rest is all good. So it's me. Yep.
Yeah, so thank you very much. So there's no time for questions, unfortunately, so we can just go for the next speaker.
If you want, I can just start from here.
Thank you very much.
Good.
You're presenting from this?
Yeah, the talk is there also.
Okay, sure.
Yeah.
Okay, so I will show you after 10 minutes, I will show 5, which means that you have 5 minutes, including questions.
Understand. Okay, thank you very much. So, as Ok-Young introduced, I'll be talking about our experimental program at Cardiff University. So if you see double here, it's not because of the heat or the wine you drank over lunch. We have, in fact, 2 interferometers identical. But before I get to that, so the legacy of this comes from, or the experimental paradigm idea comes from the so-called holometer that was an experimental program at Fermilab, brought to life by Craig Hogan and his team. And so over the years, this produced quite some nice results, upper limits in the search for quantized spacetime and other results. So the idea is you take 2 Michelson interferometers, you call them co-located, but they are as close to each other as possible. And then each Michelson interferometer is a very sensitive lens measurement device, which is how they measure gravitational waves. So you send a laser beam into two perpendicular directions and then reflect it back, and you can measure tiny phase differences that translate into displacement. And so in the search for possible quantization of space-time signatures, this acts like measuring kind of a random walk phase noise signal as the beam propagates in each arm, which is different in each arm, and so you would have a net signal, for example, from quantized space-time. So when this was discontinued, we all sat together and thought, how can this program go on? And the idea was to continue this on a tabletop scale with some extended technology. So we were trying to get more power in the interferometer, make it more sensitive. And the tabletop idea is, of course, to have it more flexible. And as we'll see, or was already mentioned, in particular flexible with changing the geometry of the interferometer, which can test different models, quantized space-time. So this was our initial idea from 2018. It's also a platform to test squeezed light sources, so engineered quantum states in the interferometer. So there are different ideas that can connect to this. So this is just an example of a modified geometry. We have a beam splitter. These are Michelson interferometers, but one arm is bent already. That already had been done by the holometer group as well. So this was our concept paper where we claim we can have better displacement sensitivity than the holometer by more laser power and using quantum states of light, squeezed states of light. And so this is the first instance of this experiment that is running now, which has been implemented. So these are, as I said, Michelson interferometers. The initial arm length here is 2 meters. Then we have a power recycling mirror that is just to build optical resonator to increase the circulating power to make it more sensitive. So we sent in 10 watts of light, and in the final configuration we aim to have 10 kilowatts operating here, and then we read out these interferometers with photodetectors. And here's just an image. Experimentalists like to show images of their experiments, as you know. So this is the interferometers you see here with vacuum beam tubes. So it's operating in vacuum, and here is preparation optics and laser, and here's a squeezed light source from our collaborators in Germany, from Max Planck. So we just published our first results, kind of interim results. They will be published in a few weeks by PRL. And so these blue and green curves are individual sensitivities. So the workhorse quantity of figure of merit for Michelson interferometer is the displacement amplitude or power spectral density of displacement, meters per square root of hertz. So we can measure displacement fluctuations at some frequency of 10 to minus 18 meters. So this is the initial phase. In the future, we'll try to go to a few times 10 to minus 19 meters. So these are the individual interferometers, but the real power or beauty of having two next to each other is you can cross-correlate them. And so you get rid of all independent noises. You integrate your signal over time. So it has the assumption that your signal is stationary over time, which would be true for quantized space-time noise. And so with the cross-correlation in this first run of 10 to the 4 seconds, we reached here a sensitivity a few times 10 to minus 20 for cross-correlated noise. And we didn't find any, so which is indicated mostly by this variance here, but also by some other analysis that we did. So far this is good because there are no technical correlations, but ultimately we want to get more sensitive to test models. So as a side product, because this is a mini gravitational wave detector, we can translate this displacement sensitivity into strain sensitivity to gravitational waves, actually. So these are new upper limits in this range, which didn't exist before. Here are limits from the holometer, but this is a bit of a side product. And another interesting measurement that can be done here is to do the cross correlation not between two interferometers, but do the cross correlation between two photodetectors reading out one interferometer. And that allows you to get rid of the quantum noise limitation as well for any stationary noise in your interferometer. And so this is a very nice measurement. This forest of peaks here is actually the thermal eigenmodes of the 1-inch mirrors in the interferometer. So it's quite a novel measurement, at least for some of this frequency range, which demonstrates like the power of the cross correlation technique. So our future directions are, for one thing, to use quantum technology, so actually apply squeezed states of light. That hasn't been done on our tabletop yet, but we have the squeezed light source ready to do that. And then we also want to do something new, which is photon counting as a readout. Instead of using continuous wave photodiodes, it's possible to read out, or we think it's possible to read out individual photons only of the signal sidebands, and that can be more sensitive for stochastic sources, which has been shown in a number of papers over the last years. And then we want to scale up, as Okyung already mentioned, to 5-meter scale. So here's our new lab and the table ready, which then will allow to test some models. So here is an optical layout with some more detail about the single photon readout. So we take the outputs of the two interferometers and interfere them, which just allows us, depending on the relative phase between them, to construct a channel which has either signal or no signal. So we can make null measurements, switching between these two paths. But then if we want to measure the signal, we send it to a series of optical filter cavities, which reject all the carrier light that arrives here, and then only passes the few photons per second or less which carry actual signal. And so these will be filtered by these, and then we have single photon counters for that. So that's a side remark on the technology you want to use in the future to be more sensitive. And Okyung showed this. So this is an example of a 3D geometry of the interferometers. So in the first step, one can change, for example, the angle of the Michelson interferometers. So here are the beam splitters, and these are the two arms of Michelson interferometers. And there are also different predictions for how quantized spacetime noise may couple to the interferometer for different angles. But then to test, for example, one particular model, we want to extend these arms into the third dimension. And so, this could look like something like this, because it's more complex to develop some structure in 3 dimensions which would be stable enough against vibrations and things like this. So this is what we can target with this 3D geometry, for example. So this is one of the predictions that Okyung mentions in this work, shown in this graph. So it's a signal which has a certain structure in frequency range, and in blue and red here are the sensitivities of individual interferometers. This is the expected thermal noise floor, which is relevant for the single photon readout. But with the cross correlation technique, then we think we'll just be able to bridge these several orders of magnitude to probe this noise floors here in a few years from now. So that's the plan for the for the next steps. And I mentioned gravitational waves as a byproduct, and of course, again, these are very highly sensitive experiments. So it turns out they are also sensitive for scalar field dark matter, for example, which can affect or would affect the fine structure constant and thus the size of objects. So we also have a side stream of work with this where we reinterpret data from existing gravitational wave detectors in terms of searching for scalar field dark matter and also for vector field dark matter. So there has been a series of publications on that, setting new upper limits on scalar field dark matter. Okay, so here's our current group in Cardiff, and we also have a postdoc position right now. If you know of anybody interested in this kind of works, then please contact me. Thank you.
Yeah, but that is just for the online audience, not for us.
Thanks for that talk. I was curious about how high your powers are getting compared to like a scale where you can see noise coming from radiation pressure on the optics.
Radiation pressure is not so relevant here because we measure at higher frequencies. It might be relevant maybe for the thermal modes, but it's different from gravitational wave detector where the optics are suspended, and they look at a few tens of hertz where radiation pressure really moves the mass. But this is below. I mean, we are way above this frequency range. So our limitation is purely shot noise, which then we benefit from using squeezing just in squeeze light in just one quadrature.
Yeah, over there.
So two questions really. First question is kind of yes or no. Is it correct that you have effectively the same kind of same order of magnitude of sensitivity as LIGO, just at higher frequencies? Is that correct?
Yeah, so the displacement sensitivity we can reach is a few times 10 to minus 19 meters. That is similar to LIGO from a few years ago. So LIGO can now reach close to 10 to minus 20 meters. But of course, that is just the displacement.
Yes.
So that's independent of the arm length. But for gravitational waves, then LIGO is much more sensitive because it's a product of sensitivity and arm length. But yes, I mean, mostly the sensitivity of microscope interferometer is given by the power you have. So we have 10 kilowatts. LIGO now has a few hundred kilowatts, but it goes with the square root, so it's a factor of several, but not an extreme difference. Yes.
Okay, and then that feeds into my second question, which is, I'm sorry if you maybe you covered this in the first couple of slides, which I missed, but if say you do see something, how do you know that it's not, for example, stochastic gravitational wave background or something like this, something classical, but still interesting, of course?
Yeah, that's the key challenge, which also faced the people from the holometer team, that eventually you may find some correlated noise, and of course you first have to try to look for if it could be of any technical nature. And yeah,
I mean, I would argue this is still an interesting measurement, even if it's not quantum. But
yeah, of course, but this is where signatures of your predicted signal can help. But ultimately, then, if you find a candidate and can't find any technical explanation, you need a second experiment to validate any big discovery. And so yeah, we have a there's another program going on of the same kind at Caltech, which is called GQuest. Ours is called Quest, and so we would have a complementary experiment looking for the same thing.
Okay, thank you.
Yeah, let's take a look again.
Sorry.
You can also modulate the signal. I have to plug it somehow.
Just keep it there. experimental.
Oh,
It doesn't
perfectly.
move the slides, it only works as a
Okay,
pointer.
okay, thank you.
Isn't it yours?
No. I can take mine before.
Do you have your talk on a computer?
I have it on USB, so maybe anyone can borrow a computer. Perfect.
So maybe you can from the other side?
Sure.
Maybe let him do it because he knows this.
Yes.
His device best.
That's not. Okay. Oh,
That's it, right?
that's it. Perfect. Where's it? Maybe.
What is the shortcut for full screen in Acrobat Reader? Control L.
Okay.
Thank you.
Thank you. Thank you.
All right, so after 10 minutes I show you 5, and that this includes the question time, right?
Okay. Does anyone know how to remove this? Do you know how to remove those? Okay, so maybe I can just start with this one. Maybe we can open it with some browser, this file.
No, we can even close and restart the
Sure.
program.
Perfect. Thank you very much. Thank you. I'm very excited to present you my recent work. I did it with Kacper Dębski and with a small help of Andrzej Dragan in University of Warsaw. It's about the problem that we face when we want to create relativistic theory that is also quantum one. There's a problem of ordering of operators, and I want to study this particularly with small connection to thermodynamics. And as you can see in the future, we have some possibly experimentally testable predictions from this type of procedure. So first of all, when you look, when we start just from the classical relativistically invariant form for energy, I've just assumed that the G0 I is equal to 0 for simplicity, but in principle you can have some values there. There is this ambiguity that you multiply metric by momenta, and this metric is a function of position, and when you want to quantize a system, you have a non-trivial commutation relation, and usually what is assumed is this Wigner-Weil scheme of quantization. For example, it's also known as polynomial quantization, when you just symmetrize your operator with some constants here that in this case are just equal to 1/3. But in general, it's arbitrary. There is no obvious way how to, what is the most general formula. The first problem that we face is that when you look at this square root, this time dilation term, you can either multiply the square root from left or from the right side onto this dynamical part of this formula. And there are two conditions that your Hamiltonian has to satisfy. For sure, it has to be Hermitian, which is the first condition, and the second condition is that when you go to classical limits, so when you make your operators commuting, you should recover the classical formula for energy. So when you plug it with some arbitrary constants, from Hermicity you see that this one has to be the conjugation of this gamma here, and from the classical limits, the real part of gamma has to be equal to 1/2. And 1/2 is exactly the case of Weyl ordering, but in principle there can be also some imaginary part to gamma that is not present in the standard Weyl form. Then when you look at the spatial part of the metric, we again have to see the same problem. Now, for simplicity, I have assumed that we only have momentum in the radial direction, and here R is some reference position, let's call it classical, and there is small quantum perturbation from this reference position. So first of all, GRR in general is some function of position, so we have to expand it in Taylor series in order to make it reasonable somehow physically. But then you have this type of term. So a position operator to the kth power multiplied by momentum squared, and this has to be ordered properly. And in principle, you can add some arbitrary constants alpha, beta, and gamma to the those terms with momentum on the left, momentum from both sides, momentum from the right. And from Hermicity, you see that gamma has to be equal alpha squared, and beta has to be purely real. And from classical limits, alpha plus beta plus gamma has to be equal to 1. And when you perform this algebra, you obtain the result on the bottom line. And as you can see, those three arbitrary parameters now become only one parameter, alpha. We have some term where we can determine just the imaginary part of this alpha and the whole alpha, so we can determine it in detail. So the theory is based on two parameters, arbitrary gamma, which orders the time-like part of the metric, and alpha, which orders the spatial part of the metric. Let's simplify even further. So let's go to the low energy limit and assume the small perturbation in position. And we have this Hamiltonian where the first term corresponds to H0 is the inertial Hamiltonian, so it can be mc squared, for example, but also a two-level system or any system that you want to study. Then there is this part with linear potential. In the second line, you have kinetic energy plus some correction to the energy from the curvature. And those first and second line are purely classical terms. When you expand it to in this limit classical formula for energy, you get exactly those two lines. However, the third line, which is dependent on those ordering parameters alpha and gamma, doesn't appear in any classical form of Hamiltonian. We can simplify even further. So we can assume that our metric is the simplest one, so it's the Rindler metric, where all spatial dependence is just trivial, is equal to -1, and the time dilation term is linear in x. So now we do not have to perform this Taylor series expansion because we have linear term in position operator. And we can write explicitly, and as you can see in this central line on the screen, this is the Hamiltonian, which is relativistically invariant and has some quantum degrees of freedom of position and momenta, and is dependent on some internal Hamiltonian H0, which is dependent on this complex parameter gamma, which is this ordering parameter with respect to the time. You can study this if you want to. However, in order to deal with those square root of p squared and the last term on the right, it's quite hard. For example, if you want to calculate specific heat, you get some functions that do not simplify easily, so I've assumed even the next simplification, so just the low energy limit. And this is the Hamiltonian that you obtain. And further idea is as follows. We calculate the spectrum of this Hamiltonian, we calculate a specific heat from the spectrum, and then we have some dependence on gamma, which is this ordering parameter. And in principle, by measuring specific heat, we can obtain the real physical value of this ordering parameter gamma. So this is actually not important, it's easy. You just have your standard Hamiltonian, which is Hamiltonian with linear gravitation term. It's known, it has known solution at the Iry basis, and you add this quantum perturbation, relativistic quantum perturbation, and you can calculate the first and second order corrections to this energy. The zeroth order is just mc squared plus Iry zeros multiplied by mg multiplied by characteristic length. The first correction doesn't depend on gamma, so actually it doesn't give us this physical insight that we want to study, but the second order correction is explicitly dependent on gamma, and this gamma parameter works like somehow mixing those an are the Arya zeros, so it somehow mixes energy of another coming from another energy levels. Okay, so when we study specific heat in relativistic scenario, we have to be precise in what we mean by temperature because of the redshift or the Tolman-Ehrenfest relation. So there are going to be three plots actually. The first one is just based on the assumption that the heat buff is placed in exactly the same place where we have our setup. So there is no redshift scaling. The temperature is just equal to the temperature of the heat buff. But in principle, if you want to, you can assume that your system is at some proper distance from the heat buff. As you can see here, the system in blue, the heat buff in red, and you have some scaling resulting from the Tolman-Ehrenfest law. And we calculate numerically, unfortunately, the CV0, which is just taking the zeroth and first order that do not depend on gamma, and then the proper specific heat, which does depend on the second order correction to gamma, to energy, sorry. And these are the plots. The dashed black line is this CV0, so this, let's call it semi-classical approximation of specific heat. It reaches this placebo at exactly a Boltzmann constant. Is this specific heat per the number of atoms? Exactly at Boltzmann constant, so as one would just obtain from this, from the phase space integration of the, the semi-classical approximation of the partition function. As you can see, the red line corresponds to Weil ordering, the green line corresponds to Weil ordering, so gamma equal to 1/2 plus some arbitrary imaginary constant, and the shapes of those curves are different. The experimental problem is that the values of acceleration has to be quite extreme in order for this to be visible. So in the case of electrons, this is achievable currently, accelerating electrons to this type of acceleration. However, in case of gravitational interaction, in this system you would have to take neutrinos and be near some very extreme black hole. This is really there is no black hole with this type of acceleration in the near universe. However, so this is the drawback, let's call it. However, the nice thing is that there is this paper that you can see at the bottom where they have calculated specific heat from the Klein-Gordon equation in Rindler frame, and the shape of specific heat curve was exactly, had this quite the same behavior as you can see here. However, their work was not it was a different setup that was not depending on those ordering parameters. Right, and here is this other setup. So this is the theory is exactly the same. However, now we place our heat buff at x equal to 0, so in the center. And when you are at some proper distance from the heat buff, you have temperature, your temperature is scaled by the Thomann law, and the curve looks like this. There is also another possibility of creating this type of experimental measurement. Summing up, the idea is that by measuring specific heat at unfortunately extreme acceleration and small masses, one could in principle determine what are the real physical value of ordering parameters in the quantization problem of relativistic theory. And there are maybe few problems that I would like to mention to you now. First one is that this whole derivation was based on assumption of the Boltzmann gas. So we are above condensation temperature, we're above Fermi level, so there are actually no nice quantum results, but we want to extend this to this type of setup because I believe, for example, there might be a change in critical temperature. The second thing is that this Tolman-Ehrenfest law here is assumed as the classical scaling of temperature with respect to position. And in principle, one could think of scaling, of defining quantum temperature operator. There is some work regarding this, but I don't know it yet, so let's just leave it for the future works. So these are just takeaway messages, but maybe right now I can hear your criticism and questions and so on. The paper unfortunately is not, the preprint is not yet available. It should be available tomorrow or anything, but if you want, there is my mail, I can send it to you if you want to read it. Thank you.
Hi, thanks for the talk. So I do have one question. Like the way, correct me if I'm wrong, but I think the way I understand this is the problem with ordering that you have kind of comes from the fact that you are considering relativistic quantum mechanics rather than quantum field theory. So is it like, does it make sense to consider relativistic quantum mechanics for these kind of problems that you are solving later with the acceleration and the specific heat?
There are many works working, for example, on like this Unruh Witt detectors or studying some atomic interferometry or two-level systems that are using this low energy approximation of QFT, which is quantum mechanics, and this is something between, so it's a bit farther than standard quantum mechanics, but it's not full quantum field theory. I don't know, it's interesting to me. I can't ask you if it's, I can answer if, yeah.
Okay, thanks.
Let's thank Carl again. And yeah, but we don't have time, so you can discuss later. So there's now hopefully Shamila. And you sent her the link?
I already sent her the link.
Mm-hmm.
Shamila?
I think she's not online.
No, she's not. Yeah.
I think you just started the meeting, right? So.
She should be there.
She's logging in now? She's already in the waiting room. Oh, yeah.
Oh, yes.
Ah, she's in the waiting room.
Yeah.
Okay, cool. Okay. Shamila, can you hear us? Can we hear her? Is that now streamed through the speakers? Ah, hi Shamila.
Hi, sorry for the inconvenience before.
Okay.
again. Is it visible?
Oh. Ah. Yes. Now it's good. Okay, perfect. So, great. So we have the first talk of the session now at the end. Thanks for waiting. And Shamila, the stage is yours. Please start.
Thank you. Good evening, everyone. And I sincerely thank the organizers for giving me this opportunity. Despite the initial visa trouble which prevented me from riding in vehicles with you guys, and also now my horrible connectivity issues which delay this talk. Thank you for the patience and thank you for this opportunity. Now, to my talk, I'm going to talk to you about I'm Sajnok from Grote, and I'm going to talk to you about my current work, which is computing of correlations with space-time fluctuations from interferometric outputs. This is work done in collaboration with Sajnok and animation from Relativistic. This is recently being put up on the archive, so for anyone who's interested, the archive number is there on the slide now. Also, it's there when this is discussed. Now, this is a brief overview of the talk, where I first motivate what's the cause of space-time fluctuations, and then talk about how it affects the interferometric output, and also identify characteristic signatures of different gravity models and the role of correlations in identifying such characteristic signatures. Finally, summarize the two main results of my talk. Now, where does space-time fluctuations first come about or first proposed in what context? It is proposed in the context of vacuum fluctuations in the gravitational field. For any bosonic field, as it's very obvious, quantum vacuum is not a complete absence of bosons, but rather random creation and annihilation of bosons. In the context of electromagnetic field, for instance, the effect of the vacuum fluctuations was first observed in Lambda measurement and Lambda Ford experiment, which laid practically the foundation stones for quantum electrodynamics. So detecting vacuum fluctuations was first thought of as detecting quantum physical field, and in that context, it was proposed by Wheeler as space-time fluctuations, later known as space-time form, where it is seen as space-time fluctuations which are Planck field, which are say superimposed on the wind of CEST. Now, space-time fluctuations are not limited to this particular application of gravity. It's a phenomenon that is almost made belief in various different projections of gravity, starting from related quantum field theories to holographic models to models which are semi-classical in the sense that we have gravity as a classical field but with stochasticity to account for gravitational equilibrium, or gravity seen as an isoscopic emergent phenomenon, or in cases where gravity is seen as a classical emergent phenomenon from underlying quantum entanglement or holographic degrees of freedom, and also in the context of the stochastic gravitational wave background. Now, when a phenomenon has so many theories that are proposing it, it's obvious that the underlying statistical properties of these fluctuations will be dependent on what gravity we are thinking about. So, for instance, the correlation function, which is proposed by each of these theories of gravity, would be very different, and even the correlation length scales from, say, Planck length and effective quantum field theories to long-range correlations in holographic models. So, studying the role of correlations of space-time fluctuations in the expected experimental output is very important. In fact, if you want to build a theory where you want to have a situation where you can read off signatures which are specific to various gravity models, then it's important to build a catalog of expected experimental output for different kinds of correlation or forms of correlation functions. So, what do I mean by experimental? One common platform that's being used for research and the study of space-time fluctuations is
this is now Emanuele Panella who's going to speak, and yeah, everything is running, I guess.
It seems running to me.
Okay.
Cool. Actually.
The stage is yours.
Yes. Hello, everyone. First of all, thank you to the organizers for inviting me to speak about my work. I am going to talk about nothing that is quantum and nothing that is information, unfortunately, but I hope the motivations are good enough such that you will buy that this fits somehow into relativistic quantum information. In particular, I'm going to talk about work that I've been doing with my supervisors, Jonathan Oppenheim and Andrew Ponset at UCL. And the topic will be cosmological tests on the quantum nature of gravity. And the motivations are quantum information based. So somehow over the years we have always given for granted that we need to quantize the gravitational system for consistency. So essentially there is just a series of no-go theorems that tell you that if you have classical system and quantum system interacting with each other, you incur into some type of contradiction, and those arguments can all be easily circumvented once you realize that there is an underlying assumptions into them. Well, maybe the most famous one is of these theorems is from Feynman at the Chapel Hill conference, where you look at some type of generalization of the Spenger-like experiment where you couple your electron to a classical gravitational field. But the idea here is that unless you assume that classicality and determinism are the same thing, then all these no-go theorems actually fail. You can go around them. And classicality actually does not equal determinism in many classical systems. Usually those are effective in nature when we talk about the stochastic force that sources them, but nonetheless you can imagine some fundamental classical degree of freedom, which is classical in the sense that it just undergoes some objective trajectory in phase space. So this is going to be essentially my definition of classicality, and if you give me that, then you can actually come up with a lot of consistent classical quantum models, and historically just Thawing model came up, just simple examples, and then there was a more complete characterization of this type of dynamics just in 2020, more or less. And what turns out is that if you want to take some classical degree of freedom interacting with quantum degrees of freedom in a consistent manner, then not only you need to allow for some classical diffusion, some classical stochasticity, that classical stochasticity needs to be there. So you just cannot get rid of it. Actually, not only that, but also the quantum system must decohere. So this is something we call the coherence diffusion trade-off. Essentially, the classical degree of freedom undergoes just some mean drift, some mean evolution, which is whatever you want to do. It might be coupled to maybe the expectation value of the quantum degree of freedom, but on top of that, there is some noise, and the size of the noise is controlled by maybe this parameter sigma of z, which can only depend on the classical degree of freedom, and this is crucial. The quantum state also needs to give up unitaries. So you might have some unitary evolution and then some decoherence terms, but the strength of the decoherence term is inversely proportional to the amount of noise. And you can imagine this type of system is essentially as measurement and feedback. So the classical degree of freedom acts as a measurement device on the quantum one. The worse the type of measurement it does, the less the coherence you have in the quantum state, but then also the more uncertainty you have in the classical back reaction. So this is the idea behind it. And what I am going to do is I am going to just assume that gravity can be treated in a fundamentally classical way, and therefore must have some type of stochasticity in its evolution, and ask whether this is consistent with cosmological observables. So I'm trying to come up with essentially a proof of the quantumness of gravity by contradiction. So I try to understand what is the phenomenology associated with a consistent fundamental classical theory of gravity at the level of the cosmological observable, and see whether it's in the data, essentially. So let's just review very quickly the simplest cosmological model we have, which is lambda CDM, FLRW in particular, where we assume that the universe is homogeneous and isotropic. Once you make that assumption, then the system trivializes, essentially. You just are left with one single degree of freedom, which is the scale factor A, essentially the radius of the universe, and that undergoes the Friedmann's equation. Here I'm going to work in the Hamiltonian formalism general relativity because it's easier to add stochasticity in a 3+1 formulation of GR. And so I have just split up the FLRW equation in the first equation is just a definition of the conjugate momentum to my scale factor, so there is nothing interesting going on there, and all the physics is in the second equation. But this is not enough. GR has diffeomorphism invariance, and this is very crucial. And the way diffeomorphism invariance appears in the 3+1 formulation of general relativity is through constraints. So algebraic relations between your fundamental degrees of freedom that need to be satisfied at all times and are preserved by the GR equation. In particular, when I'm looking at cosmology, all the constraints just actually collapse to a single one, which is called the Hamiltonian constraint. It's called the Hamiltonian constraint because the thing that has to be 0 on shell is essentially just the Hamiltonian of the system. So it's somehow you can imagine it as the energy of my gravitational matter system. So here I'm assuming all matter has decohered, and then under the assumption that gravity is fundamentally classical interacting with quantum fields, it has to be stochastic. So I'm going to stochasticize this system, and because the evolution of the cosmological history has been 14 billion years, the diffusion away from the GR deterministic solution might be significant over cosmological timescales, and we're actually going to see that indeed there is something that is going on once I stochasticize the system, which is non-trivial. So let me stochasticize the equation of motion. I cannot do much. I'm very much constrained by the symmetries of the problem. Here, the only, let's say, gauge freedom that I have is time reparametrization invariance. And the only way that I can preserve that symmetry at the level of the equation of motion is by adding the term in red, where this C is just a mean-zero process with some variance, which is for now just model dependent. It's something that is not given to me for granted just by looking at the equation of motion. I need to pick that. I just know that has to be a scalar of A and pi A. And then it's delta correlated in time. So how do I use this? How do I choose this D2? Well, again, here I need to make some assumptions, but usually what you do in cosmology is that you start from the universe is actually not homogeneous and isotropic, it has inhomogeneities, but you trade time evolution and averaging. So usually the zeroth order approximation is that you treat the system as homogeneous, so you average over a spatial slice and then you evolve in time. And I do the same. I just need to choose the averaging surface, and here I just use the causal patch that is in contact with with the patch of the universe that I'm looking at, essentially. So I average over the Hubble scale, and when I do that, I find that during inflation, essentially, my diffusion coefficient with respect to the local diffusion of the local stochastic theory is just constant. Whilst if I go into radiation and matter domination and assume small diffusion, then what happens is that the effective cosmic diffusion drops in time. So over time, the noise is going to decouple from the homogeneous evolution, and it's just going to be present at the level of the linearized perturbation, for example. But from the global point of view, the system is just going to be deterministic. Okay. Now I'm going to do a very quick aside on stochastic processes. It's going to be very, very quick because it just relies on some very easy physical intuition. So imagine I have just some free particle undergoing Brownian motion. So essentially the same situation as before. I have P dot, my momentum is sourced by some white noise process, so mean zero and delta correlated in time. On the right there, I have some sample paths of the trajectory, but you can easily see that essentially the average of the momentum at all times is zero in this case. Is P is equal to P0, so the momentum doesn't change. But of course, this is not true for any combination of my stochastic variables. So, for example, the energy, which essentially just the variance in the momentum, is going to increase, is going to spread in time, and actually this physical intuition is just very well mathematically grounded in something that is called Ito's lemma, which is the cornerstone of stochastic dynamics, that says that if I have some complicated function of my stochastic degree of freedom, because of the stochastic kicks being of fractional order in time, when I compute the time evolution of that function, I need to also keep second order terms. So, and that second order term is going to be linear with the diffusion coefficient. And you can go and essentially compute the evolution, for example, the energy of the particle, and you can see that it increases, even on average, linearly in time. And so this, again, agrees with the intuition that the energy of the particle is essentially just the variance in phase space of the probability distribution in the momentum. Good. So now we do the same. We just assume the equation of motion that I showed you before with some stochastic noise, and then we look at the constraint and say, is the constraint preserved by the evolution as it is in the deterministic case? And the answer is clearly not, because the constraint is the Hamiltonian of the system. So in analogy with the one-dimensional particle, the energy is going to go up. And it's going to go up in a positive way and linearly in time. So it's violated even on average, and you can ask how much constraint violation do I produce at different phases, in different phases of the universe's expansion. So the biggest contribution comes from inflation, when, if you remember, during inflation, the diffusion constant, the effective global diffusion constant, is constant and doesn't change in time. So I do accumulate some non-trivial positive constraint violation, and then after inflation, I have reheating, I enter radiation domination, and my diffusion constant drops as 1 over t, my effective diffusion drops as 1 over t, and noise decouples. And so now I'm left with a deterministic system with some constraint violation. But the deterministic equation of motion just preserves the value of the constraint. So that constraint is going to remain there for the rest of the universe, for the rest of the history of the universe, but it's still going to dilute because of the expansion. So I can compute essentially the energy density associated with the constraint violation, and so on and so forth. And then I can ask certain questions. Okay, so now we have a specific deviation from general relativity. I'm in a constraint system, which is not constraint anymore. I'm off the constraints. So would I have noticed that? And you can say, okay, so this constraint violation actually stays constant in post-inflationary evolution, but it does dilute with the expansion at the level of the energy density. And then you can ask what happens if I just perturb this global homogeneous constraint violation, and how do these perturbations evolve, and they just evolve and dilute as ordinary pressureless dust, so as ordinary baryonic matter, let's say, but that it only interacts gravitationally, and it has obviously no fundamental associated particle to it. And this is just called dark matter phenomenology at the level of the global expansion of the universe. And so you can take these results in 2 ways. I would say it's something that if the theory of gravity is fundamentally classical, it predicts something that adds to cold dark matter. And because the amount of this phantom cold dark matter that you get is proportional to the diffusion coefficient, you can use the observed abundance of dark matter to essentially pose constraint on the allowed diffusion coefficient of the theory. Or you can be more radical and ask whether it can actually replace cold dark matter altogether. But in order to do that, then you need to answer some short-term questions. So, for example, would you be able to reproduce by getting rid of dark matter altogether things like, for example, the CMB? And in order to do that, you need to develop some inhomogeneous model of classical quantum cosmology and understand what happens to the constraints in a more refined theory. Because here you have obviously just 1 degree of freedom, so the constraint is almost useless. It becomes important when you start adding all the degree of freedom you have in local GR, because you need to have just 2, because it's a massless graviton spin 2 field. Okay, so this is it for me. If you have any questions, I'm happy to answer them.
So we have time for 1 short question. There, please, yes. Over there. And in the meantime,
thanks for your very nice talk. You motivated why you have chosen this specific noise model, but can you say again why it's unique and why you cannot choose any other noise?
So here at the level of the equation of motion. So essentially, a white noise process is formally the derivative of a Brownian a Brownian motion, a Wiener process. So if you go under the assumption that you have continuous trajectories in phase space, then you need to be careful about how a white noise process transforms under time reparametrization. So the form of this A squared C is just constrained by the symmetries of transformation of what a white noise field does. But you are still free to choose just an arbitrary function of A and pi A as long as it's a scalar, and then that is model dependent. Supposedly the way I flow to the global homogeneous system is by just doing some averaging process. But of course you can, this is in the effective model, you're free to choose it as long as it's a scalar. Yeah.
So thanks again. So you can put that on. And is there supply somewhere?
I think it's weak.
10 minutes, I show you 5.
Yeah, okay.
But that includes your
my questions too. Yeah, okay.
Okay, so the next talk is Panella. So
yeah. Do I need to use the microphone or?
yeah, exactly.
Okay. All right, thank you. Yeah, so I will be talking about my research, which was in collaboration with André Grote and Kamal Deuner. So what I will be talking about is a thought experiment that was originally proposed by Mario et al, or maybe more famous from a paper of Balamurugan et al. So let me just jump right into it. So the thought experiments, on the left side we have Alice, who has a system, which he brings into superposition of being left or being right. After some time, she can combine them again and she gets an interference pattern, as long as nothing happens to her system, right, by complementarity. On the other side, we have Bob. In this case, Bob also has a particle which he brings in a superposition. It will evolve freely, but it will interact through some Newtonian potential with Alice's particle. So it will accumulate a phase over this time. After some time, Bob will also bring his particle together, and he can, for example, do a spin measurement, and from that, he can determine the path of Alice. Basically because he has to accumulate this phase, but this phase is depending on the position of Alice's mass, of Alice's quadrupole moment. So he can get which way information of Alice's system. Now by complementarity, this means that if Alice would try to mesh her system, she could no longer find the interference pattern. In this way, Bob can basically send 1 bit information to Alice. If this happens in a time shorter than the distance, they will break causality, or they will break complementarity. Either way, there is some problem here. So there has been some solutions to it. For instance, if Alice would bring her particle too fast into a superposition, it would radiate and it would already break her interference pattern. So she would not find the interference pattern regardless of what Bob does. It also goes for Bob, of course. I will also go into some bounds on the mass that will be important for us. So let's have a look at Bob's side. So Bob will start with a state given here, where chi is this is the total state. The chi is the state of Alice's system. D, big D is the position, and this is a spin in a Z eigenbasis. Then after a time, like I said, here, his particles has accumulated a phase due to the interaction with the Newtonian potential. So Q is the state of Alice's, for a quadrupole being on the left or being on the right. D is not interesting, that's just the position. It's all about this phase. So big gamma here is the phase accumulated when Alice's particle is just in the middle, so that's not the interesting part. What I really want to focus on is the small gamma here. So the small gamma here is depending on delta Q, where Q is Alice's quadrupole being on the left or being on the right, the difference between it. Furthermore, tau E is the time of Bob's entire experiment when the optimal trajectory has been taken. and the rest are just constants. So to optimally distinguish between Alice's quadrupoles, we want to set gamma to pi1/2. So we're going to plug in pi1/2 there, and then we can set a bound on the mass of Bob. So the mass must be larger than this times the Planck mass. That is necessary for Bob to accumulate this phase difference fast enough to be in a time shorter than the distance, to allow for causal breaking, basically. Yeah, I will try. Okay. So on the other hand, we can also think about, at the end of Bob's experiment, he's going to do a measurement of this, of his spin. So we're going to look at Bob's system. So here we have this operator that he will measure, and he will get two results out of this based on the quadrupole of Alice's quadrupole being on the left or the right. So here A is the off-diagonal terms. For the small gamma, we still have pi1/2. So this is basically 1 minus A and 1 plus A. And obviously, if A is 0, then he gets the same result. And he still cannot say if Alice's quadrupole moment is on the left or on the right. So we don't want that. We want this to be as large as possible. And that happens when A is 1. So we can see here it goes exponentially down in terms of time. So we can expand around that, and we're going to set that to 1. And then again, we can set a bound for the mass. So he also assumed that Bob cannot instantaneously do a measurement. It takes some time to do the measurement. So that's delta t. Now this delta t, you can try as small as possible, but we said that he at least needs a Planck time to do his measurements. So we can also set that as a bound, and from that we can also set again a new bound on the mass. So now we have two bounds for the masses that we can combine. The first mass was needed to accumulate a phase fast enough for superluminal signaling, and the other one was required because he needs a Planck time to do his measurements. If we combine those together, then we get that the small d must be larger than about 6 times large d. And this is of course a problem. If we look at the schematics again, you see small d was basically the difference from Bob's Robocop in the center, while large d was the difference between Alice and Bob. So if big D is smaller than small d, then Alice is inside Bob's experiment. And that breaks it down, of course. So this is not possible. So this seems to solve the paradox and then save causality again. But if you notice, we worked with a constant mass over the whole time. But gravity does not just interact with mass, it interacts with energy. So we can replace the mass, basically, with a total energy, which also is an internal energy, which does have to be constant over time. We can change, we can play with that. So then we can see, can we try to create this paradox again? And how would it then be solved? So we want to basically replace the same equations. So this is the first one that we have, but we change the mass for the total energy, and we assume that the acceleration timing is much, much smaller than the time of the free flight. So we can basically, we can ignore this, and we're just going to say that the first excited state has to be larger than this time to the Planck energy. From the second one, from the measurement time bound that we have that the ground state must be smaller than this. So now we can say, okay, what kind of, for hypothetical atom do we need in a lab that would have these energy states? So first we can just use the standard expressions for these energy levels from a hydrogen atom, and then we can combine it. We get that you need a right back energy larger than this, where the big M is the sum of the masses. Furthermore, we can look at the Bohr radius, which we also say has to be larger than the Planck mass. And from that we see that the total sum of masses must be larger than about 2 times the reduced mass. If we have this, then this should theoretically be allowed to have superluminous signaling of breaking of complementarity. Now, to make an atom like this in a lab is extremely challenging, of course, but there's nothing fundamentally stopping us at this moment. So we're going to think about, okay, how can we save this? So there are a couple of solutions. So first, what you can ask, is the excited state and excited, is it stable enough, or will it already decay long before Bob can finish his experiment? Well, we can look at two different radiations, gravitational or electromagnetic. So for the gravitational case, it's quite simple to have a jump in by by gravitational radiation, then the quantum number L must be the difference of L over 2. So if we would just excite to a p shell, then yeah, this would not be a problem. For the electromagnetic case, we can look at the transitions rates. So the absorption and the stimulated emission rate, if you would look at that, then this is depending on the photon number n. While the spontaneous emission, it is not. So we could just have a very, very large number of n, which would make sure that the absorption and the stimulated emission at the end would be really, really fast, and we don't lose much of the time with that. But we can set the other parameters such that spontaneous emission would not be a problem, that it would stay in the first excited long enough that Bob can finish actually the experiment. Furthermore, hidden effects. So this is one of the solutions that was already in the original paper being proposed by Arya et al. Is that there is perhaps some unknown intrinsic mechanics outside of quantum mechanics that we don't know of that would prevent this from happening. Yeah, perhaps, I don't know about that, but that could still be the case. Maybe more obvious ones is that we can think about decoherence. So this was also a solution for the first time. As I've mentioned, if Alice brings her particle in a superposition too fast, or else for Bob, then it will radiate and it would already destroy the interference pattern. So she needs to do this slowly enough. But we can also think about if Bob's system would be excited, there will also be a displacement of mass, there will be a momentum kick. And we can think also about getting radiation from that, which would destroy his particle. Or we can think about that Bob would already get rich wave information about his own system, which he cannot finish his experiment and not get rich wave information about Alice's system. So these seem to be likely solutions. So radiation from the absorption. We can think about something else. We can think about, this is an article by Pikovsky, that talked about decoherence from time dilation, where he also looked at multi-particle systems in the Newtonian potential of Earth, and then also found that if you get difference in proper time and you get decoherence from internal and center of mass coordinates. You can basically look at the same thing here again, although we would expect this to be extremely tiny in the case of just the Newtonian potential of just an atom. So this is likely not going to be any problem, not save our problem. We expect it to be a decoherence effect, or we expect to be something that Bob can already find which way information about his particle long before he can finish his experiment, and that will break it down. So why this is very interesting is because the gravitational case is very different from the electromagnetic case. In the electromagnetic case, all the previous bounds that has been set would already solve it. We don't need all this. It is really only from the gravitational case that we get this problem again, and we need something else. We need to add something to solve the paradox again. And it's interesting because we kind of work just in the perturbative regime here, where we usually can write the gravitational case completely analogous to the electromagnetic case. But here this doesn't seem to be the case. Okay, well, I was already at the end, so now it's time for questions, and I'll thank you.
So there's time for at least 2 questions. So there are some questions from the audience. So it's not good knowledge. So you thought now about Rydberg atoms, right? That was what I got.
Just hydrogen-like atoms. Yeah.
Yes. Did you also think maybe about nuclear transitions, nuclear excitations?
No, that we don't know. No.
That might be interesting. There now they are controlling at least one of them in the lab now for nuclear atomic clocks. And they have really a large coherence time, so maybe that would be something.
Oh, that's very interesting to look at. Yeah, well, thank you. Thank you.
So, some questions? All right. So if there is none, let's think.
Thank you.
Can you put it on your t-shirt, please?
Yeah, sure.
You take the microphone, and for 10 minutes I give you a sign.
Okay.
And then you have 5 minutes left, including our questions, right? So our next talk is by Arya. So the stage is yours, please.
Hello everyone, my name is Navdeep and I am a postdoctoral researcher at Stockholm University, and I'm going to talk about bridging general relativistic gravity with quantum systems, and we propose to do that by having a lot of quantum systems team up together to act as a better sensor. So usually the kind of effects I'm going to talk about, they are very weak on single quantum systems. So our basic proposal is to have these quantum systems act together and be better sensors for these effects. So as examples, I'll talk about two of our recent works. In one of them, I'll consider a gravitational wave, and I'll show that a gravitational wave can induce superradiance in a bunch of atoms. In the second one, I'll talk about Unruh effect, which doesn't include gravity directly, but it can give insights about gravitational situations as well, and it is interesting in its own right. So let's start by talking what happens when atoms act together. So I have a plot for photon emission intensity on the y-axis, and on the x-axis I have a dimensionless time. If you have n excited atoms and none of these atoms care about each other, so their photon emission process in time would look like the blue dashed curve. It will be a monotonic curve, the usual exponential curve. But if you bring these atoms close enough, they start talking to each other, and then they can decide to emit their photons in a synchronized manner. And that's when you get the red curve, and it is known as superradiance. So there are some features of this curve that are of interest to us. First of all, so in these systems, you can use a figure of merit, which I am denoting here by mu times n, where capital N is the number of atoms that you start with, and mu is some modulation factor which accounts for imperfect conditions. For example, if everything is perfect, mu would tend to 1 minus 1 over n. So basically it becomes 1 for large number of atoms. So you say that all of the atoms in your sample are cooperating with each other. If there is no cooperation, mu tends to 0, and you get the usual dashed blue curve. And the two interesting features of this curve are, there is this delay time. So you see that the photon emission rate can scale quadratically with the number of atoms in the sample, but the maxima occurs after a delay time, TD. And moreover, this enhanced photon emission rate survives for a short time period, which is known as superradiance time. And just to summarize everything up, superradiance is a tool that combines three features in a single tool. Amplification, because photon emission intensity can scale quadratically with the number of atoms, or in more simple words, it can scale better than linear scaling with the system size. Second, sensitivity. So this delay time TD that you see here, it is very sensitive to the field fluctuations that these atoms see in their initial time of evolution. So it can act like a very sensitive tool. And the third one is these atoms can talk to each other and decide to emit their photons in a short time window. So they synchronize their photon emission process, and we'll see how we can benefit from this. So just to give you an intuitive picture, what happens is that you have two atoms and they are coupled to a common electromagnetic field. They are not directly coupled to each other, so they can talk to each other through the electromagnetic field. And this process is quantified by Gij. It is known as the Green's function. So it basically tells you that if some atom here does something, how likely or how much of it gets to some other atom in the sample. And so the mu n, effective number of cooperating atoms, are highlighted here in yellow. So what you do is you basically pick all the crosstalk between these atoms in your sample and sum them up, and you normalize by 1 over n, and you get the total number of cooperating atoms. So the game is to make mu n stronger. We want a lot of atoms to cooperate under whichever phenomena we are trying to detect. So first of all, let us consider gravitational waves. So we consider a plane linearized gravitational wave. It comes along and meets these atoms on a plane. And because now you need to quantize the electromagnetic field on a curved space-time due to the gravitational wave, it changes the Green's function. So it changes the way these atoms talk to each other. And so Fij is the part of Green's function which dominates energy exchange between the atoms and the field. So in flat space-time, the crosstalk between atoms is governed by the sinc function. So it basically says that you need to have these atoms close enough so that they can talk to each other and can do all the interesting things that we saw in the previous slide. Then the gravitational wave induces a cooperation where here h plus is the amplitude of the gravitational wave, omega is the frequency of the gravitational wave, and this Fij with superscript GW is the crosstalk that the gravitational wave induces between these atoms. And perhaps this is the most important slide for gravitational wave induced superradiance. So in plot A, what I am doing is, in blue you see flat space-time crosstalk between atoms. In red you see the crosstalk induced between the atoms by the gravitational wave. And if you zoom in, you see this perfect sinusoidal pattern. So it is basically a cosine. You can dig deeper into the equations and you find a cosine. So if you compare the sinc function to the cosine, sinc suppresses like 1 over x. So if you move these atoms far apart, the flat space-time cooperation between them goes down and they stop talking to each other. But the gravitational wave acts like a common phase reference between these atoms, and it allows distant atoms to talk to each other. So it is like a waveguide. So if you had coupled these atoms to a waveguide rather than they being in free space, the sinc would have been replaced by a cosine. So it would have allowed distant atoms to talk to each other. Now in B, I zoom in a bit to these crosstalk functions, and the dashed green lines are where we put our atoms. So now we are selecting the separation between the atoms in a 1D array, and at these locations, the flat space-time crosstalk between atoms vanishes. But the gravitational wave induced crosstalk is maximum at these points. So in C, I am showing that once you choose this interatomic spacing, this is the crosstalk you see. The flat space-time crosstalk, blue one is 0, and the crosstalk due to the gravitational wave is constant up to some point, and then it falls off. So you keep on putting more atoms in your array, and as your size of the array exceeds half of the gravitational wave wavelength, they stop talking to each other. So the fall you see here marks that point. So it is the gravitational wave kind of acts like a waveguide, but that waveguide has a maximum length as well. So now the game is simple. The gravitational wave connects these atoms together, and now they can cooperate due to the gravitational wave. And now this cooperation will lead us to a superradiance-like signal. Just to summarize, in this setup, the atoms would have 3 signals. First one is where none of the atoms care about each other. So they are going on emitting photons independent of each other. The second one is the usual one that you see in quantum optics under the term superradiance, and you can kill it here. And if you operate your array with d of the order of the transition wavelength between the atoms, only collective effects that your array will pick up are going to be due to the gravitational wave. So, okay. So basically from this slide, let us take the message that the flat space-time superradiance and gravitational wave-induced superradiance occur in different regimes. For flat space-time superradiance, you need the interatomic spacing to be much less than the transition wavelength of the atoms. But for the gravitational wave-induced one, you need d to be of the order of lambda naught, and that's important. This slide just says the same thing. In A, I show you the superradiance induced by the gravitational wave, and the dashed curves show you what is known as superradiant beats. So you'll see the photon intensity coming out of this sample beating at the gravitational wave frequency. And on B and C, I saw this transition from gravitational wave induced superradiance to normal superradiance. And if you are worried that this may be very fragile, here I'm showing that the position disorder in current day optical lattices or tweezers, at that position disorder, the flat space-time cooperation does not revive, the gravitational wave induced cooperation does not go away, and perhaps that can motivate a new way of detecting gravitational waves. So this plot is somewhat schematic in the sense that it includes only photon short noise, position disorder in an optical lattice, and atom missing from their sides. So now let us quickly move on to our next example. So Unruh effect is a prediction which says that if you have isolated observer, it will perceive inertial vacuum as a thermal state. And in particular, the photon emission and absorption rate satisfy this condition known as the detailed balance condition at the Unruh temperature, which is directly proportional to the acceleration. Now, people usually talk about absorption rates because they are kind of noise free, because if there is nothing to absorb, the absorption rate would be 0, but the absorption rate is exponentially suppressed. Alternatively, one could look for signatures in emission rates, which are stronger, but they have a lot of inertial spontaneous emission noise as well. So what we are asking is, can we resolve the Unruh, the acceleration-induced correction to the emission rates against the overwhelming inertial noise? So I talked about the superradiant delay time. So I'm showing you these states. Basically, if you have all the atoms in the excited states, you start at the top of the ladder. And spontaneously, one of the atoms would emit a photon, and the system cascades down these states, which are known as Dickey ladder of states. So before the system can give you a superradiant burst, it needs to acquire enough correlations. And these correlations take time, which is given by the superradiant time. And this time is very sensitive to the field fluctuations that the sample sees during its initial time of evolution. Can we use this fact as a sensing tool? So this is our setup where you have two parallel plates and an array of atoms. The blue curves show you the stronger crosstalk between atoms when they are accelerated under the conditions that are marked here. And the thinner yellow lines show you the crosstalk between atoms even if they are not accelerated. So without going to too many details, so the idea is, if there is Unruh effect, the accelerated sample would see stronger field fluctuations and it would acquire the correlations needed for superradiant burst much earlier than an inertial sample would do. And if that happens, you will see a superradiant profile like this. So you'll get a blue superradiant peak much earlier in a Rindler sample of atoms as compared to an inertial sample of atoms. So that's what we are calling time resolved and superradiantly amplified Unruh signal. So the idea is to say that if there is Unruh effect, you get a superradiant signal much earlier than an inertial sample or inertially perceived vacuum fluctuations can lead to. And at the same time, you get this n-square enhancement of the signal. So basically, the Unruh signal would be separated from the inertial noise both in time and intensity. So there is a trade-off between, so you can do it at low accelerations if you can give me a cavity with high enough quality factor. So we talk about this very important aspect where there is a trade-off between the acceleration requirement and the cavity quality factor that you can supply. You can take a look at that in our paper. So maybe this is the message you can carry with you. This is the graphical summary of this Unruh effect work, where you identify requirements to time resolve and amplify Unruh signal, and So if the atom is accelerated, the acceleration allows it to couple to a broad set of field modes. And if you have a sub-resonant cavity, you can suppress the inertial channel of crosstalk between the atoms while the Rindle channel still survives, and it should lead you to an early superradiant burst as a signature. Just to summarize, I am saying that gravitational waves can allow distant atoms to talk to each other electromagnetically, and this leads to a new phenomena which we have termed gravitational wave-induced photon superradiance in atoms. And you can use superradiant delay time as a sensing tool because it magnifies field fluctuations, and it should give you a time-resolved and superradiantly amplified Unruh effect. Thanks.
You used all the question time, but thank you.
Yeah, thanks. Thanks.
There will be enough time, right? You're going to be wrong.
Yeah, sure. Oops, sorry.
Can I put it on you? Oops. Thank you.
The same as like.
Right.
Okay.
So that's the microphone
okay.
for the room.
Okay, hi.
And I will show you after 10 minutes, I will show you 5, that you have still 5 minutes, but that includes your question time, right?
Okay, sounds good. Okay.
Okay, so the next talk is by Maria Rosa Preciado-Rivas.
Yes. Hi everyone. I'm a PhD student at the University of Waterloo, and today I will present a project titled Simulating a Superposition of Spacetimes using Optical Media, which is a work in collaboration with Germaine Tobar and Magdalena Saik. I would like to acknowledge that I stutter, which means that I may repeat certain words and certain syllables during my talk. There are many approaches to a theory of quantum gravity. None of them are very satisfactory, but they have in common that the laws of quantum physics are maintained. So if gravity is quantum, then space-time is also subject to the laws of quantum physics, meaning that it can also exist in a superposition of classical states. The approach to study these superpositions in RQI is a bottom-up or phenomenological approach, in which they consider an unreadable detector that is coupled to a quantum field whose background space-time exists in a superposition. The detector becomes entangled with the field and the metric, and when they trace out the field's degrees of freedom, we are left with the state of the detector, which is going to correspond to the probability that the detector will undergo transitions between its energy states. Because the detector was entangled to the field and the metric, then it will be some decoherent state because it will lose information to the other subsystems. And this decoherence is what we consider to be a signature of the superposition of spacetimes. With this approach, they have studied, identified Minkowski and Riedler spacetimes, de Sitter curvatures, and even black hole masses. Now, shifting gears, analog gravity explores systems that can mimic these gravitational phenomena or curved spacetimes. There are many classical models and quantum models to study phenomena like the Hawking effect and the nature of horizons. And there are also analogs for superposition of spacetimes. The first model is a Bose-Einstein condensate, in which they have a superposition of particles being in one of the wells or the other. And there's another model in which they consider two rotating Sajnok interferometers, which was originally designed to entangle path and polarization, photons degrees of freedom. And they claim that they can have a superposition of spacetimes inside the fiber loops. And that's about it. There are very few analogs for superposition of spacetimes, which means that there is plenty of room to further explore. So today I bring a proposal for anarchy, or analogs for RQI. And the key ingredient is the permittivity of optical media, which effectively slows down light. There's already a established analogy between the electromagnetic field in curved spacetime and the electromagnetic field in an optical medium. So we want to use a superposition of spacetime, a superposition of permittivities to simulate a superposition of spacetimes. We start small and we consider one mode of the electromagnetic field with some permittivity epsilon I, that is the Lagrangian, which depends on the electric and the magnetic field. And we have the Hamiltonian, where Q and P are given by the Maxwell's equations. And we can see that the dynamics of the mode are going to depend on the cavity's permittivity. Doing the usual quantization, we can write the Hamiltonian in the usual harmonic oscillator way, in which we have that term for the number of excitations, but the frequency of the mode is going to be modified by the permittivity. Now we have the cavity with one permittivity and with another permittivity. We know that the modes for these permittivities are going to be related by Bogoliubov transformations, which are equivalent to having some squeezing, where the squeezing is going to depend on the value of the permittivities. Using this, we can learn that the vacuum state for a permittivity which is symmetric, which has symmetric fluctuations, is going to be equivalent to a squeeze state in the cavity with another permittivity. Now, we consider the cavity and a qubit, which is in the plus state. And we have this evolution. That is, the field evolution is going to depend, or is going to be determined by the permittivity, which at the same time is going to depend on the state of the quantum qubit. In this way, we can achieve this superposition of permittivities. Now, what we do is to measure the quantum qubit along some superposition basis, and we get that the mode is going to be in some decoherent state, which is going to be a superposition of squeeze states. We investigate what is the mean of the number operator, that is, what are the excitations with respect to one of the permittivities, and we can see that that mean is going to depend on both permittivities. Using this, we can calculate what is the Mandel-Q parameter, which basically compares what is the variance and the mean of these excitations in the cavity. When there is no superposition, you can see that epsilon 0 and 1 have the same value. Then Q is larger than 0. Actually, it is always larger than 1. And this is because the cavity is just in some squeeze state. And the distribution, meaning that the mean, that the variance is going to be larger than the mean, can be interpreted as some classical state. But when there is a superposition, we can see that the Q parameter as a function of time presents these maxima and minima, which is the signature of the decoherence. And we have checked that these peaks coincide with the peaks in the Vogt-Neumann entropy of the control qubit. And another feature is that Q can also have some negative values. That means that the mean is going to be larger than the variance, which corresponds to a sub-Poissonian distribution, which tells us that the state of the qubit is going to be quantum for some time. At first, we were surprised by these results, with Q being negative, but just earlier this month, Assisi published an article saying that you can actually achieve anti-bunching, which corresponds to this negative Q using a superposition of squeeze backward, which is what we were doing too. There is a way that we might be able to take this to the lab. We came across this experiment or this framework that is called vacuum-induced transparency, where they consider lambda-type atoms which are driven by a quantum cavity in a way that they can make the group velocity of a probe field to depend on the quantum state of the input probe pulse. And in 2011, they were actually able to do this. They were able to change what is the transmission and the group velocity of a medium using only a few photos. So we were very excited to hear about this, because if you can change the group velocity, that means that effectively you can change what is the permittivity depending on the state of some quantum system. Finally, I want to draw the analogy between the RQI framework, where we have a detector, a field, and a space-time, and between our system, which is the cavity with some permittivity and the control qubit. The permittivity and the control qubit are going to have the role of the field and the space-time in a superposition, and the state of the on-route detector is going to be analog by the cavity or by the excitations in the cavity. In this way, having a superposition of constant permittivities might allow us to simulate the behavior of an on-route detector that is in a superposition of Minkowski space-time with different speed of light. I will leave you here with some acknowledgements, and I want to thank you for your attention. I think that we can hear Everett. Well, I don't know.
No, but it's just for
okay.
the screen, so it's here.
Okay. Well, I'll act like it's on. I was wondering if you could go back to the Q versus energy gap plots. I was wondering whether there's like some way of understanding where the resonance peaks occur. Like what is the significance of this, like 20 or like 65? Like, is there some way of understanding why these numbers are special?
Short answer, no, we don't know why yet. The thing is that in order to get these plots, we expand the squeeze states into number states, and then we need to apply the, maybe I have some backup slides. And then we need to calculate what is the effect of the Hamiltonian I on the J states, where J corresponds to the other permittivity. So because we need to expand the squeeze states into number states and then do these operations, we end up with many series. So we still haven't been able to track down where the peaks might be coming from, but that is something that definitely we need to look at.
Are there any other questions? This is not working.
I wonder about those permittivities being put in superposition, or even group velocities. How they kind of seem like microscopic things. How you feel they will be in a superposition? How long will they stay in superposition, and how will that manifest?
Yes, it is like, I know what you mean. If we have a superposition of permittivities, that is like having a superposition of cats, right? But that is what they might be able to achieve with this experiment. The goal of doing this experiment is to be able to separate number states. So they have the laser, which is a superposition of different number states, and then they are trying to separate them in order to have these one-photon sources. So we still haven't looked into this a lot, but it seems that it might be able to have this group velocity that depends on some quantum state. Yeah.
Okay, so let's thank Maria Rosa again. So you have to take that microphone.
I'm not sure how.
Get it off. And then that's for the other audience. This one is for the room.
Okay.
You have to connect your computer. Maybe get a bit closer to the machine.
Yes, one moment.
Yes, and then after 10 minutes, I show you 5, which includes your 5 minutes include your
The time for the answer.
Question time.
The questions, yes.
Okay. So the next speaker is Marchese, and the stage is yours.
So, hi everyone. Before I start, I just want to thank the organizers for putting together the conference, and also thank you for having me here. Today I'm gonna talk about cascaded optomechanical sensing, and I would like to start by giving you a hint of how we can use optomechanics for sensing purposes. So some of you might be familiar with optomechanical cavities, but here you just see a simple sketch where essentially we shine some light in between two mirrors, and one of the two mirrors is attached to a spring. So this means that when the light impinges on the mirror, because of the radiation pressure interaction, the mirror will be moving. And this interaction actually gives rise to a lot of interesting features, but what we are interested in here is to use these sensors, these systems as sensors. And this can be done because essentially, if you cool down your mechanical mirror to the ground state, then you can actually enter the quantum regime, meaning that the mechanical motion will be highly sensitive to any small disturbances. So imagine you have an unknown signal that is affecting this mirror, then by detecting the light, you might be able to infer something on this signal. So
Of course, the challenge is that you usually don't have only one signal, but you have a lot of noises that will also displace your mechanical motion. And then if you want to use these systems as sensors, then you need to distinguish which signals comes from the source you're interested in and which one comes from the noise. And typically, the force that comes from the signal of interest is very small. So the challenge is extremely difficult. But a little bit more in detail, what can we actually sense? So I will give you one example. So we say that this can be used as very sensitive detectors. And one example could be then to apply it to the gravitational field, because we all know it provides like a very small forces. So, for example, we could look at the gravitational field sourced by the Large Hadron Collider, where we have a ring of and some bunches of protons that are accelerated in this ring. And these particles, they move at very high speed. So, meaning that we are entering a new interesting regime, the ultra-relativistic one, and we can use these particles as a source of gravitational field. Now, the important thing is that when we are in this regime, when particles move really close to the speed of light, then the gravitational field is effectively similar to the one sourced by a laser beam, because the contribution coming from the rest mass energy is negligible. And why this is interesting? Of course, first things is because it's in a lab experiment, so you can have control on that. But also because exploring this regime is actually new, so it's still uncharted, and might lead you to test or even constrain different theories for gravity. So, as I mentioned at the beginning, the challenge is to distinguish the signal of interest from the noises. So we want to get an enhancement. And in general, one way to do so is to copy your system multiple times, performing n different measurements on each of the system, taking an average. And then, if you want to estimate some parameters theta embedded in your system, then the variance associated to these parameters will scale proportionally like 1 over square root of n. Other way of getting enhancement could be, for example, correlating probes. It has been seen that entanglement and squeezing can lead you a further enhancement known as the Heisenberg limit that tells you that the variance of your parameter will scale like 1 over n. The problem is in general that if you want to implement this in an experimental scenario, then you are strongly limited by the number of systems that you can use, because the coherence will play a very big role, and any quantum resources is very sensitive to the coherence. So you cannot extend it to too many n systems. So what we suggest here is to use a different scheme. So using coherent averaging. We have still n copies of our system, but instead of performing n individual measurements, we couple all of them with the same quantum bus, and then we perform a single measurement on the quantum bus to extract information, the parameter theta, encoded in your systems. The advantage is that you can still have accumulation of the phase in this quantum bus, so you might be able to reach this 1 over n scaling for your variance, even by just using product states of your systems. And it comes like quite clear that then this scheme is more robust under the coherence. So how do we use this scheme with optomechanical system then? This leads us to the part of cascaded systems. What we want to do is to place n cavities and optomechanical cavities next to each other, and using a pulse, a laser pulse, to couple all of them. So the pulse will go through the first one, then with some optical elements is directed to the second cavity, so on and forth until it reaches the detector. So in this scheme, the bus is represented by the laser pulse. And the optomechanical cavities will be the n copies of your system that will encode the parameter you want to estimate. So imagine you have some signal. This will displace all your mechanical elements. And you will have accumulation of this space over the multiple sensors. In the end, you want to read out your laser pulse. And the goal is to then estimate the signal-induced modification of this mechanical motion through a readout of the laser pulse. So we also want to use pulsed optomechanics. So this means that we want to shine like a narrow pulse into all of the cavities. And the pulse has to be short with respect to the mechanical period. But also we want this to be longer with respect to the cavity. So tau here is the 1 over tau is the width of your pulse. And we also want to be in the unresolved sideband regime, meaning that we want a leaky cavity, so the cavity decay rate kappa is larger than the frequency of your mechanics. And then, I'm sorry. And then you want to do parameter estimation. So you want to extract information on this parameter encoded in your mechanical amplitude. And you have tools coming from, I apologize again. You have tools coming from the from metrology. So you can use the Kramer-Rao bound, which gives you the ultimate bound for your variance in terms of the quantum Fisher information. And since we are in a regime where everything is Gaussian, we can also use Gaussian formalism and describe everything in terms of first and second moment. So displacement vector and covariance matrix. This gives a formulation for the quantum Fisher information just in terms of these two quantities. And if we also want to if we want to consider, for example, a classical signal, we can just replace the operatorial description of the mechanical part as a time-dependent function. So this Q here essentially is the amplitude of this function that you want to estimate, because this will be affected by the signal you want to detect. And then in this case is a little bit simpler, because the displacement vector then will be given just by the expectation values of your output field, the laser field, and the covariance matrix is just identity. So the quantum Fisher information is given by just the derivative with respect of the parameter Q of the output field. And the results in the ideal case scenario shows that the quantum Fisher information scales with a factor proportional to n squared in the ideal case. So no losses included so far. And this is good because this is the same scaling as the Heisenberg limit. Of course, we want to include also losses, and this can be done by inserting beam splitter between the different cavities and including losses between of them. And by including this transmission rate eta, then we can repeat the same formalism, and what we get is a quantum Fisher information that still scales like with n squared, but there is also another factor. I'm sorry, it's not visible with the sunlight, but there is another factor here that is eta to the power 2n. So there will be an interplay between these two terms, and meaning that you can extend the number of your system to get an enhancement in the Fisher information up to a certain point, after which then this will not bring you any advantage because losses will increase as well. And just to give you a visual idea of what I mean by that, so this is the variance, and is plotted as a function of n's of your systems for different values of this transmission rate. So the bottom line here, the blue one, is the one without any dissipation. So there will be no minimum in this curve. But when we add a little bit of dissipation, we see that, so first of all, the variance increases, And then there is a minimum for all of these curves that is reached at different values of n. And also the variance, as I was saying, more losses means like worse estimation, so the variance increases as well. And yes, this is just to conclude that there will be an optimal value of n that will be given by this interplay between the losses and the enhancement that you get by increasing the number of your systems. So to sum up and conclude, this is a sensing scheme that employs cascaded optomechanical cavities that can be applied for gravitational field, but also other applications. The enhancement can be reached by using coherent averaging, and I showed you that in the ideal case, this goes like n squared, and in the lossy case, there is this other factor that you have to take into account. But other applications could be, for example, distributing these sensors. In the example of the LHC, you could place them along different points to get more additional time information. Or other application could involve a detection of dark matter or collapse models. I mean, the scheme is general for any signal that is weak. And I also want to mention last work that we've been doing with NAPDIP and also other collaborators of using the same mechanism for getting some enhancement in the mechanical part for getting an effect that is similar to superradiance. And with this, I just want to acknowledge my collaborators, and I also want to thank you all for your attention.
So there is time for one question.
So in this lossy case, did you compare how your procedure, is it better or worse than using squeeze state?
Is the question that using squeeze state, if it gets...
In lossy case, isn't it better to use squeeze state than probing these cavities one by one?
So I don't know, like if you use a squeeze state of the light, this could give you an enhancement, but also squeeze states are very sensitive to losses. So So yeah, I don't know because we haven't looked at this case with the squeezing light pulse, but could definitely be interesting. I don't know if it gets better.
They're not exclusive. You can just put squeeze light into it, right? So the schemes are non-exclusive. You can just do what you say, squeeze light in addition to
the pulse.
Right, but as I said, you can do both at the same time. So then, yeah, let's thank Marta again.
You have to give this as well.
And now let's come to the last talk of the session by Joshua Vogt. So, yes, you can take the clip microphone.
Yeah.
And so that's for the online audience. Okay.
I'm just wondering if it's better if I...
Yeah, I thought so. Yeah. But I'm not sure now. It's moving further up and up the whole time. So I'm also not sure.
Maybe that's fine.
Yeah. And it's also getting darker a bit, hopefully.
Yeah.
Okay, so you can
so this clips.
You clip that somewhere, and then you take that one. And yeah, so after 10 minutes, I'll show you 5 minutes, which includes your...
Yeah. Thanks for the introduction, and I want to thank the organizers, I guess we're not here anyway, but for organizing this conference and for giving me the chance to speak. My name is Josh. I did my PhD at the University of Queensland with Tim Ralph and Magdalena Zick, I then did a postdoc in Igor Pikovsky's group at just outside New York City, and at the beginning of the year I moved to Canada, where I'm now a postdoc at the University of Waterloo. I just want to do a brief advert for Achintia's talk tomorrow. He's my PhD student, and he'll be talking about some interesting connection with between canonical quantum gravity and low energy models. So my collaborators on this work were Gabe Sorchi, who's an undergrad at Stevens in Igor's group, Christian Sano, who's our experimental collaborator, and of course Igor. And so this work, which is sitting on Christian's desk, is motivated by the extreme precision that optical clocks have been able to achieve in resolving frequencies at the fractional uncertainty level of 10 to the minus 19. So this is exemplified by, for example, this experiment in Junyi's group, where basically they can trap these atomic clocks in this optical lattice and resolve the gravitational redshift that's consistent with GR and the predictions of Einstein's theory over a millimeter. Nevertheless, all measurements to date are compatible with a semi-classical model in which these quantum systems evolve with respect to some external parameter. Now, we know that in quantum theory, time is an external parameter, but in relativity, time changes, and it depends on momentum and your position in the gravitational potential. So we ask the question, are there quantum signatures of time that are accessible to clocks in which the evolution parameter, some tau, cannot be interpreted as just a parameter, semi-classically. So I'll talk about 5 models for relativistic clocks and rule them out one by one in terms of them sensing some quantum signature of proper time, and then go to our quantum model. So for an experimentalist, an optical clock is just a charged particle that is trapped in some harmonic potential, and we can model it as just following some classical equation of motion. We can average over its kinetic energy, and via the equipartition theorem relate it to half kBt. Now, so these clocks are basically trapped by lasers, and they are interrogated to read out their frequency, and these are the frequency standards that are used to basically define the SI unit of the second. Now, there is a frequency difference between the frequency of the laser, which interrogates the clock in the lab frame, and the frequency as viewed by in the rest frame of the clock. So this is related by some Lorentz factor. And if we expand this to leading order in small velocities, then we get a frequency shift that is proportional to the average over the velocity of the clock in this harmonic potential divided by 2c squared. And this is consistent with what we would typically expect for kinematic time dilation. And this average occurs over the interrogation period with which we're basically radiating the clock with our laser light. And so plugging this back into our average kinetic energy, we obtain this frequency shift, which is the so-called second order Doppler shift. It's not really second order, it's not really a Doppler shift either, but nevertheless this is what experimentalists call it. And this basically forms one component of the systematic errors that come into these experimental atomic clocks. And so this can be interpreted semi-classically insofar as you can imagine the clock basically shaking in the trap with some velocity distribution. And these are given by some thermal distribution. And so even though this is a quantum mechanical sensor, so I haven't used any quantum mechanics to derive this result, this can be interpreted as a classically derived effect. So what this means schematically is that basically they would read out the probability of finding the clock in the excited state after doing some Ramsey interferometry, and then they would interrogate and try to narrow down the transition frequency of the atom of the clock to find its frequency to define time, and this second order Doppler shift contributes to basically a frequency shift of the whole fringe relative to the actual atomic transition. So now let's derive this frequency shift from a Hamiltonian formalism that can still nevertheless be interpreted semi-classically. So let's model our clock as a two-level system. We derive some Hamiltonian with relativistic corrections as follows. So what we do is we start with some harmonic oscillator. We have a rest energy contribution, mc squared. we promote this mass to an operator that depends on the internal energy, and then expand to leading order in 1 on c squared. So the resulting Hamiltonian in equation 6 now has a clock contribution, which is hc. We have a contribution to just the pure motional dynamics in the trap, and then a clock motion coupling that basically will entangle the internal and external degrees of freedom of our system. So this promotion of the mass to an operator follows from the mass energy equivalence, and basically says that excited clocks are heavier. They couple to gravity, they couple to momentum. Obviously this is very heuristic, but there is a way to derive this from first principles using a Lagrangian and fully covariant framework. So yes, the mass energy equivalence implies that these excited clocks are heavier by some energy that depends on the transition frequency. So this generates the time evolution as follows. So we have some clock dynamics that is basically your free evolution of your clock on the Bloch sphere. There's also a squeezing term that arises due to the fact that we have this quadratic coupling between the internal and external degrees of freedom, as well as the usual trap dynamics with some modified frequency lambda. And so I've just defined these operators. These are actually acting on the joint Hilbert space of the internal and external degrees of freedom. So these are essentially internal state dependent squeezing and rotations in the phase space of the motional degrees of freedom that depend on internal energy as well. And I've just defined this small parameter epsilon, which is a comparison of the clock energy with the rest energy of the clock. So let's just suppose, for argument's sake, that we ignore the squeezing terms for now. We get this reduced dynamics, which is just harmonic evolution in the trap with some new frequency, lambda omega. So the fact that we include this modification means that our harmonic evolution occurs with some new motional frequency that also depends on the internal state. So we start our clock by preparing a superposition of grounded excited states. And let's just say the motion is in some thermal state of the trap, and then the reduced state of the clock becomes this complicated sum over all different Fock states of your harmonic, of your motional degrees of freedom with some frequency shift in each component that depends on the level of the energy level of the motion. And we can compute the off-diagonal element, which is basically the ticking rate of the clock in the trap. And we can, in the high temperature limit, derive this exact same second order Doppler shift that arises in the experimentalist derivation of this relativistic correction to the dynamics. So this can be interpreted, therefore, as a semi-classically average proper time. So let's just suppose that rather than some Hamiltonian evolution, we just say that the off-diagonal element rotates and it's with respect to some mean tau rather than some operator valued tau. We expand this Lorentz factor in the mean to leading order in 1 on c squared, and we get exactly that same frequency shift that arises in the experimentalist derivation. So we can think about this as though we've got some classical distribution of velocities in the trap. Of course, this is not the real quantum picture, but we say that each run of the experiment, the clock starts with some new velocity that's some Gaussian distribution. And this frequency shift still persists even if we take the motional state of the clock to be a quantum state. So let's say we ground state cool the clock in the trap, and then we still find that there is some correction to the clock evolution. And this is because essentially the ground state of the trap is not a momentum eigenstate. So you still get a distribution of momenta as you sample the velocities each run of the experiment. And so this is on the order of 10 to the minus 21, this vacuum SODS, and so this will become relevant in next generation atomic clocks. And again, even though we have a quantum motional state of the clock in the trap, this can still be reproduced by the same semi-classical model in which we say that the clock evolution occurs with respect to some fixed parameter. So a generalization of this leading order expansion is the more general clock evolution, which is actually a mixture over all possible classical motions in the trap. So this expression arises as some 1 on c squared expansion of this more general average over all different energies of your clock. So we get some more complicated frequency shift if we compute this more general expression, equation 15. But again, and again, this reproduces the second order Doppler shift in the small epsilon and high occupation number limit. But nevertheless, even though this looks rather strange and complicated, this frequency shift can be interpreted as a classical effect, where essentially averaging over all possible initial motional energies of our clock, and this is essentially an averaged effect over the classical distribution, and that's the only thing that's relevant here. So far we have seen 3 models, and finally I'll discuss a purely classical a model of a clock, which is just a harmonic oscillator in a trap that ticks as it swings in the trap. And if we include relativistic corrections to its dynamics, it gets a correction to its period. So we found this problem in Goldstein's classical mechanics book, which solves this relativistic harmonic oscillator. This means that it affects its frequency. And moreover, if we solve this in some classical, this classical problem with some fixed initial classical energy, we also find that its amplitude in the trap changes. So this is a kind of manifestation of dynamical length change. And this will be relevant in our quantum model, which is as follows. So if you are attentive, you would have recognized that the Hamiltonian dynamics induces squeezing in the motional degrees of freedom of our clock in the trap, and we interpret this as essentially analogous to this classical effect where a harmonic oscillator that is relativistically corrected undergoes an amplitude change as it swings in this harmonic potential. And so if we include this effect, then the dynamics evolves into the following. So let's just suppose we ground state cool our clock into the ground state of the trap, and we prepare a superposition of grounded excited. Then we obtain this semi-classical clock evolution, which can, as I explained earlier, can be interpreted as occurring with respect to some fixed parameter. But we also get excitations to the n equals 2 Fock state of the motional degrees of freedom. So this is very unusual and probably unexpected. It's as though because our clock starts ticking, its length changes, and now that its length changes, it sort of back reacts onto the ticking rate of the clock. And so we get this anomalous contribution that occurs at order epsilon. So this is like some excitation of the motional states due to the quantization of the proper time. And this length change that arises, this excitation to the n equals 2 Fock state, it can never arise if we treat time dilation as occurring with respect to some fixed parameter, or time evolution as occurring with respect to some fixed external parameter. This excitation or this squeezing of the motional degrees of freedom that depends on the internal state can only arise if we treat tau as an operator rather than as some averaged classical effect, or averaging over semi-classical trajectories. So what we do in our paper, which is, as I mentioned, sitting on Christian's desk, is we propose a protocol to extract this signature. So basically we apply some quantum control of the clock using light-matter interactions. I won't go into the details, it's not extremely relevant. And now rather than averaging over all motional states of the clock, we now want to interfere these two contributions. So we want to basically project onto 0 plus 2, a superposition, coherently. So in this way, we're essentially interfering time dilation and length contraction, which I thought was a very nice selling point of our paper. And then we perform Ramsey spectroscopy to read out the frequency shift that arises. And we get a new frequency shift, which we dub the quantum SODS, which is close to state-of-the-art experiments. And this work is in preparation. I will say that close is a theorist's definition of close, which is roughly 5 orders of magnitude away from state-of-art experiments. But we are discussing with D.D. Leibfried, who's an expert at NIST on these trapped ions, to find some intermediate results that can witness this this quantum time dilation effect in near-term experiments. So I just want to recap with these 5 different models of our relativistic clock and point out this quantum one, which I've illustrated there. Essentially, we ground state cool our clock and it evolves coherently into a superposition of 0 plus 2. And this is the quantum effect that can only arise if we treat tau as an operator. So I want to thank you for your attention, and yeah, welcome any questions.
So maybe one very short question.
You say about tau being a parameter, but do you also, I didn't catch in your formula, do you also include it into the e to the power I Hamiltonian times t? What is the time there? How do you include it as a parameter into the evolution?
Yes, so we basically start with some relativistic Hamiltonian, we exponentiate this, and then we can factor it basically using some decoupling theorems. We get this clock part, which just commutes with everything. So this is just the usual free evolution of our clock that it rotates around the Bloch sphere at some frequency nu, and then this quantum part arises due to this squeezing that depends on the internal state as well.
But I mean, you have letter T inside all of your formulas, not the tau per se.
Yes, so I mean, we apply Hamiltonian evolution, which of course occurs, by exponentiating the Hamiltonian with some t, but the resulting entanglement between the motion, which is p squared in this correction divided by c squared, mc squared, and then the internal state, this cannot be interpreted as the resulting frequency shift that arises cannot be interpreted purely as though this system is undergoing Hamiltonian evolution with respect to some fixed t. Yeah, hopefully that answers your question.
So, thank you very much again. Now there's going to be an announcement by Gitano.